Hello everyone, this is the third day of the workshop and till now we have learned all about synthesis, how to set up the design data, how to run a floor plan, how to run a placement. So this is one of the core part of the 5-day workshop and it is interesting and today we will be going in depth into one of the cells. So in our example we have taken inverter as our example cell. So we won't be building the cell from the scratch, but because it might take a little time to build from scratch, so I would be pointing you to the GitHub link from where you can download the mag file, the .magic file. From that .magic file, we will be doing post layout simulation in ngSpice and post verifying every post characterizing our sample cell. We would be plugging this cell into the OpenLane flow into a Pico RV32 core, and we will see whether that happens or not. So that is really exciting, and many challenges. There can be many challenges. So that is just the tip of the iceberg. So let's begin. So before we begin with today's workshop, I would like you to notice one more thing. So in my screen, you can see that I have done the till floor plan. So one of the features of OpenLane I had mentioned earlier was that you can make changes on the fly. Say, for example, you had set your core utilization to 50, you run the flow and you observe some congestions. You might want to change it to 65 and then run the flow again. So there is an option to make changes on the fly that would be quite useful, provided that PNR flow is basically a iterative flow. So you make changes, you observe the changes and do changes again. So right now we are inside the OpenLane. I have run synthesis, I have run floor plan. So say for example, if I want to change the configuration of how my input output pins are aligned along the code. So right now my input output pins are equidistance randomly placed pins. So we can make sure that that is the case. Where is our design? Sorry, let me clear the screen. So let's go to the run. There is one run which I have, latest run. So this is the latest run. Let's go to the results folder, floor plan, and we will see a def file here. We will open where I'm basically verifying the current, what is the current configuration of pin, and magic minus T, the text file information is present. I have actually pasted it in a notepad for simplicity. You can also do that, and we will do a left read. Left is read from the merge.left file, so it will be to level up inside the temp folder. Go inside merged dot tab dot left, and we will read a def read. We are right now in that folder location, so we just need to paste this def value. So let's see how the pin configuration is right now. So this is just after floor plan. I had covered till synthesis in the last workshop video. So this is going one level back just to show that feature. So right now, if you can see, my pins are equidistant. I have selected left click mouse button, right click. So this, as you can see, the pins are equidistant, right? So this is what we had set. So I'll just quit this for now. Yes. And let's say I want to change it to some other input output pin strategy. So there are 4 strategies that are supported by the IO Placer. IO Placer is the one of the open source EDA tools which I use to place the IOs along the core. So what we can do is we will do this, and we will just take the variable that that selects the mode for the input output. So right now I am inside OpenLane /configuration folder. OpenLane configuration. So if you remember, I had actually shown you that README file which had the description of all the switches. But I think that FPIO mode, I think that is the switch for setting the input output pin strategy. So that was there in the floor plan.tcl file. So as you can see right now the value is set to 1 equidistance. So 0 is one of the modes, 1 is one of the modes, 2 is one of the modes. So it's not there in description, but yes, 2 is this. So we'll copy this variable. We select the variable and middle mouse button. So I'm setting it as 2. So that variable has been set to 2. I will do a run floor plan again. Sorry, plan again. That should run the floor plan again in the same folder. It is almost done. Yeah, it is done. Now let us check if where was it? Yeah, this was it. We are inside the same folder. We will do the same command. The def has been updated. Has it been updated? We can verify it by the time. As you can see, okay, I didn't show the pre-time. So right now this is the latest time. So we'll use the last command to see if that has been updated. So earlier it was equidistant pin. Let's see what is the pin configuration now. So I think you might have guessed by now. So the pins are now, this is one of the normal Hungarian IO pin, this is one of the algorithms. So anyway, it is not equidistant pin mode. It has been, pins have been stacked on top of one another with no space. So this is how if you want to make a change in the OpenLink flow, you reset the variables. And then you run that flow again for the values to make change. So as I was talking about earlier, this workshop is basically aimed at characterizing a cell. So the sample cell which we have taken is of that of inverter, and as you had seen in the first half of this workshop, there are different characterizations of a cell, like the rise time, fall time, propagation delay, rise propagation, fall propagation. So we will indulge into that. So before we begin that, I will do one thing. I will open a parallel terminal. So all our works are from this directory, OpenD directory, PWD.
Hello everyone, let's continue our discussion with the SPICE simulations. So till the last video we looked into a lot of theory about the voltage transfer characteristics of the CMOS. In this particular video and following videos we'll be doing some SPICE simulation and deriving those characteristics on real-time MOSFETs. Okay, we have some 350 or 250 nanometers MOSFETs already available with us. We'll try to do some SPICE simulations on those MOSFETs and see how does it look like, and what happens when we fine-tune some of the parameters that you see in the equations, in the voltage and the current equations. So we'll do with that. Before entering into the SPICE simulations, the first part is to create this SPICE deck. Okay, so we have to create this SPICE deck. SPICE deck was nothing but a connectivity information about the netlist. So it's basically a netlist that has everything. It has got the connectivity information, it has got the inputs that has to be provided to the simulation, it has got tap points at which we'll take the output and so on. So it has got everything. So the first step is to create this SPICE deck. Okay, in the past videos we had created SPICE decks for a single NMOS, for NMOS only. In this case we have to create a SPICE deck for the complete netlist, and in this case the netlist looks a bit different than what we did before. So in this case you have the PMOS over here. The symbol of the PMOS is a bit different. Initially we saw the symbol of the PMOS with a circle over here. In this case the symbol of the PMOS looks something like this, where you see an arrow which is pointing towards outside, and in case of an NMOS the arrow is pointing towards inside. There are significances of these arrows. I'll come to that in a bit from now. So this is how your PMOS looks like. This is the substrate terminal, and this is the substrate terminal of your NMOS, and this is the PMOS, and this is the NMOS symbol. And the reason we are doing this, because in your SPICE deck or in your SPICE netlist we need to define the connectivity of your substrate as well. Substrate is a potential a potential component or a potential pin on your NMOS and the PMOS or the transistors. So you need to define the connectivity of that substrate pin as well. Okay, and we also looked into the significance of the substrate pin, where it tunes the threshold voltage of your PMOS and NMOS. So we have already looked into all those. Okay, so this is your PMOS, this is your NMOS. There is a connectivity information. The source of your PMOS is connected to VDD, the source of your NMOS is connected to VSS, and you have your input voltage and you have your output load capacitor. So there is a lot of theory behind this output load capacitor. The value of the output load capacitor doesn't comes just like that. There are a lot of equations, there are a lot of theory that goes behind the computation of this particular load capacitor. But in this case, we'll assume a load capacitor value, let's say 10 femtofarads, and move on. And in the next or in the advanced courses, we'll be looking into how do we exactly get this load capacitor. Okay, so it is basically decided by the circuit that is connected, by the input capacitances of the circuit which is connected at this point. So we'll get into all those in the more advanced videos, in the videos where we're looking into the dynamic characteristics of your CMOS. In this case, we are looking into the static behavior of your CMOS. So in this case, we'll just assume a load value and move on. Okay, so we have to define the component values. The next thing is to define the component values. By the component values, I mean the values for your PMOS and the NMOS. So in this case, the PMOS is given the value of W by L as 0.375 by 0.25. It says your channel length is 250 nanometers or 0.25 micron, and your channel width is 0.375 micron or 375 nanometers. And same we are going for M2. So there is a scenario where we understand the PMOS should be wider than the NMOS, and we'll come to that, the reasons why the PMOS should be wider than NMOS. In this case, we'll just assume the values of 0.375 and 0.375 both for PMOS and NMOS. So we are taking a same size PMOS and NMOS and see what happens in the characteristics. Ideally, your PMOS should be twice or thrice bigger than your NMOS. By that I mean 0.375. It should be this should be 0.375 multiplied by 2, in that range. But there are again reasons and there are applications for both of them. You need this kind of inverter, as well as an inverter which has got a PMOS bigger in size. You need both kind of inverters for your application. So we'll get into those as in a bit from now. For now, we'll just look into the PMOS and the NMOS of the same size. Okay, and see what happens to the characteristics. And the next component value that we have to decide is the output load. Basically, we just assumed a value of 10 femtofarads over here. Basically, this value comes from a lot of calculations. Basically, the circuit that is connected at this node, the following circuit which is connected at this node, has got some input capacitances and all those things. So we have to look into and we have to compute those load capacitance. In this case, we'll assume a value of 10 femtofarads. Okay, next we'll define the values of the input gate, the input gate voltage. So we'll assume a value of 2.5 volts. So generally, if you have a node value of, if you have a channel length of 250 nanometers, usually the voltage is kept in the multiple of 250 nanometers. So in this case, it's 2.5 volts. Had the channel length be 0.1 micron, this would have been 1 volts or and so on. So it's just a calculation that happens, and I'll get into the calculations in some time from now. For now, we'll assume a gate voltage of 2.5 volts. Okay, we'll assume a drain voltage or the main supply voltage as 2.5 volts, and we'll move on. So these are the component values that we are picking up. Okay, we have these values for PMOS, we have the values for NMOS, the load capacitor, and the input and the output voltage. Input and the supply voltage. Okay, and these are all the VSS terminals. So let's club the VSS together. So we have this common VSS for all the supplies that is present over here. Okay, next step is to identify the nodes. So for example, in the past couple of SPICE videos, we have looked into what does a node mean. So in this case, node means there are those 2 points between which there is a component. For example, over here, this and this becomes a node because in between there is one component. So in order to define this component in a SPICE netlist, you need a node. You need to say that this component lies between this and this node. So that's basically a definition of the node. For example, let's look into this and this node. This and this node. So in this case, this M1 transistor is defined between 3 nodes, this node, this one, and this one. Okay, so there are basically no components connected between this node and the transistor, this transistor and this node, this transistor and this node. So there are no components defined in between them, so we can very easily define this particular transistor in between these three nodes. Okay, let's pick up another component. For example, let's say we have this load capacitor. The load capacitor can be very well defined between this node and this node, because this is a node which is common to all of them, common to the VSS common node, and you have this particular node which is present at one of the parallel plate capacitor of your output load capacitor. Okay, so there is nothing other that is coming in had there been a resistor over here, then there would have been this node and there will be another node which is present over here. Since there is nothing present between this point and this point, this can be considered as a potential node. So these nodes are basically required to define your spice netlist, and I'll show you in some time from now how basically these nodes are important. Similarly, if you look into this VDD can be very well defined between this node and this node. Okay, so let's name these nodes. We'll give this node name. We'll call this as in, we'll call this node as VDD, we'll call this node as out, and this node as 0. Since it's VSS, we'll call it as 0. So basically, if you want to define an output load capacitor, we'll say that the load capacitor lies between out and 0. If you want to define the VDD, we'll say that the VDD lies between VDD and 0. Okay, and we'll look into one of the definitions of this, but one of the applications of this particular nodes. So let's start writing this spice deck. Okay, so for example, these are just comments. Anything that starts with star are comments. So this is model description, and we'll start with the netlist description. So let's say M1, the MOSFET M1. You have the in the past video we have looked into the syntax of the MOSFET in a spice. It's drain, gate, source, drain, gate, substrate, source. So M1 will be drain, so drain is out. If you see at this particular point, your drain is out. For the M1 MOSFET, your drain is connected to the out node, your gate is connected to the in node. Okay, your substrate is connected to the VDD node, and your source is also connected to the VDD node. Okay, so this particular till this point, this defines the connectivity of M1. PMOS says that this M1 is of type PMOS. Okay, W is 0.375 and L is 0.25. So this line completely describes this PMOS transistor, which is defined by the name M1. So M1 is connected between out, in, VDD and VDD. Okay, it's a type PMOS transistor. It has got a width of 0.375 micron. It has got an L of 0.25 micron. Okay, so what we'll do is since I'm running a bit late out of time, we'll stop at this moment, and in the next video we'll continue writing the spice deck and completing the spice deck and running a spice simulation on this deck. Okay, so let's try to do all this in the next video. Thank you. Hello everyone. Let's continue our discussion on describing the SPICE deck for the CMOS inverter. So we had described already the PMOS transistor in the last video. So this was the PMOS transistor and this was its respective connectivity information. So it lies between DGSS, so drain, gate, source and substrate. In the last video I had mentioned this as substrate and this as source. So just correcting over here, it's drain, gate, source and substrate. So your out terminal, your the drain terminal of your PMOS is connected to the out node. Okay, your gate terminal of your PMOS is connected to the in node. Okay, your NMOS, your PMOS transistor source and substrate are connected to VDDs respectively. Okay, and this is the description for it. It's a PMOS transistor. I'll come to where we get this PMOS name and all, and this is the channel width and channel length of the PMOS transistor. Okay, so moving on to the NMOS transistor. So we have this we have this as the NMOS transistor, and it is connected between out, in, 0 0. So when you say we have given a name to it, it's called M2. Okay, and it is connected between out, in, 0 and 0. So drain, gate, source and substrate. So drain of your M2 is connected to out. The gate of your NMOS is connected to in node, and your drain and the source and substrate are connected to 0 node. Okay, so that's what we have mentioned over here, and it is of the type NMOS, and width of the NMOS is 0.375 micron, and the channel length is 0.25 micron. So this was about the connectivity information of this CMOS inverter only. Now we need to describe the connectivity information for others as well. Okay, so let's look into the other components. The first one will look into the output load capacitor. So the output load capacitor is connected between the out node and the node 0, and its value is 10 femtofarads, and that's what is precisely described over here. Your C load, the name of the output load capacitor, is connected between out and 0, and the value of it is 10 femtofarads. Okay, next you have the supply voltage, which is VDD. The supply voltage VDD is connected between VDD and 0. Okay, and the value of it is 2.5 volts. So that's a very simple description of your supply voltage. And similarly you have the input voltage, which is Vin, and Vin is connected between the in node and the node 0, and its value is 2.5 volts. Okay, so these were pretty simple compared to the NMOS and PMOS descriptions. So next we have to give some simulation commands. Okay, so the simulation commands come something like this. We say that so we had seen some simulation commands in the past when we were trying to describe an NMOS SPICE simulation. So in that case we had swept the gate input voltage of your NMOS transistor from certain voltage. Okay, similar thing we'll be doing over here. We will be sweeping the gate input voltage from 0 to 2.5 at steps of 0.05. So the reason we are doing is we need to calculate the voltage at the output, or the waveform at the output, while we sweep the input voltage, because that's the voltage transfer characteristics, your output voltage versus the input voltage, and that's what we are trying to do. We'll be sweeping the input voltage from 0 to 2.5 at steps of 50 millivolts or 0.05 volts, and measuring the output voltage, or measuring the output waveform. Okay, so that's what we will be doing over here. Then the final step is to describe the model file. So this is very important. If you see this particular model file, this is the one which has got the complete description of your NMOS and PMOS transistors. So all the technological parameters, all the parameters which is related to 250 nanometer technology node are all described in this model file. I'll open this model file in a bit from now. So this is the file from which it takes all the descriptions of the NMOS and PMOS. So in this file you will see an attribute called as NMOS, and all the descriptions related to that particular NMOS, all the parameters related to that particular NMOS. Similarly, you will see a keyword called as PMOS inside this mod file, and all the technological parameters related to this particular PMOS. Okay, so without wasting any time, let's try to move on and do the SPICE simulation. So we'll be doing a SPICE simulation for this particular specifications. You have WN, which is the channel width of your NMOS transistor, is equal to the channel width of your PMOS transistor, is equal to 0.375, and that's what we had seen over here. Your channel width we have kept constant. Okay,
and the channel length for your NMOS and PMOS are kept as 0.25 micron, which is again constant, and your W by L ratio for your NMOS is equal to W by L ratio for your PMOS. Ideally, we expect W by L ratio of the PMOS to be slightly greater than W by L ratio of the NMOS, and I'll come to that, the reasons, and under what conditions do we need them to be same. There are various applications for both of them, and I'll show the applications as well. Okay, so we will do a SPICE simulation for this particular scenario, and I have the SPICE window open with me. So this is the SPICE window which is already open with me. We'll start with the model file. So let me show you the model file first. Okay, so this is your model file. So this is where it has got all the description. You have the model NMOS, its name is NMOS, and these are the all technological parameters with respect to this particular NMOS. Similarly, we'll have something like PMOS also. So this is the dot model. This is the syntax of describing the PMOS technological parameters. So you have this PMOS, which is the transistor name, and this is the complete description of your PMOS transistor. So it will have all of the parameters that we described in our past videos. For example, it will have the oxide thickness, it will have the threshold voltage under zero substrate voltage, it will have all your coefficients K1, K2, K3, it will have basically, if you go through this file, I'll upload this file, you will have everything which is related to this particular PMOS and everything that we discussed in our past videos. Okay, so this was about the model file, and this is what we have included in our netlist description. Okay, so let's look into the netlist first. So we'll look into, this is the netlist. So this is the netlist that we had just described above. You have your PMOS transistor, you have your NMOS transistor, and the load output capacitor and everything. Okay, so we will do a quick simulation on this one. So we will pick up the SPICE just to minimize this. So we'll first go to this area over here. Okay, and next we have to source the circuit file. Let's do it. Okay, so now this says that when we actually source this, it says that the circuit is now present in this particular simulator. Okay, now we'll execute the circuit. The command is run. Okay, we will set plot, and when you just type set plot, you will see which plot is now currently present in your SPICE simulator. So it's a DC1, and this is the DC transfer characteristics. Okay, so we'll give DC1. Okay, now we'll look into the nodes that are the node voltages that are present to us. So we have this voltages that is currently present with us, and we have to plot out versus in, because that's what we are looking at. This is the node where you supply, and which is the voltage which you have been sweeping, and this is the output node that you want to look into the waveform. Okay, so we'll plot this and see what do we get. And this is what you get. You get a neat waveform or neat voltage transfer characteristics of the CMOS transistor, and this is the kind of waveform that we have been looking into. But if you see, this particular thing is slightly shifted towards the left. Okay, and I'll come to that why it is shifted towards the left. But if you see, this particular transfer characteristics closely represents what we described in the theory lectures. Okay, so let's minimize this. So let's move the waveform in this particular slide, and we'll move into the next kind of simulations where we have kept the NMOS width as 0.375, but we have shifted the PMOS width to 0.9375. So 0.9375 is basically 2.5 times of your NMOS channel width, and let's confirm that. 0.375 multiplied by 2.5. So you have 9375, and we have increased the width of your PMOS transistor 2.5 times than that of the NMOS transistor. Why are we doing so? I'll come to that in a bit from now. Okay, so let's try to do the SPICE simulation for this one. So let's close this, and we have a separate. This will be the SPICE deck for a similar scenario that we just talked about. Everything else remains the same except that your PMOS width goes to 0.9375. Okay, so we'll do a similar SPICE simulation. we'll go to our spice simulator. We will source, let's copy this, we'll source this circuit file .cir. Okay, we'll execute this circuit now. We'll set plot, we'll see what is the new plot that is available. So these were the past plots that were available, and we plotted DC1 for your previous case where your PMOS and NMOS width was same. Okay, in this case the current plot is DC2, and this is the case where your PMOS and NMOS transistor width vary by 2.5 times. So this is DC2. So let's set that plot. Okay, display, let's look into what is available with us. So we have again the in node and the out node which is available. So let's plot them. Plot out versus in. And yes, this is what you get. Okay, so if you closely look into this waveform and the previous waveform, you will notice a difference over here. And what is that difference? Let me try to come back on that particular difference in the next video. Just observe this particular difference, that this particular thing lies somewhere at the left side. So if this was a complete range of the voltage 2.5 volts, and if this was the center of your voltage, if this was the center of your graph, so this particular transfer characteristics is shifted towards the left. In this case, it's exactly at the middle. So let me try to give you more explanation on what exactly went in both the simulations. So let me try to cover all this in the next video. Thank you. Hello everyone, let's continue with the SPICE analysis. We did the SPICE simulations for a device where PMOS was 2.5 times greater than NMOS, and basically the width of the PMOS was 0.9375, and this is 2.5 times of your NMOS. So we did that for a purpose to show the difference in the SPICE characteristics. So we'll try to analyze this particular SPICE waveform. For that, what we'll do, let us keep these two waveforms side by side. So we have in this side, we will have the SPICE waveform for Wn equal to Wp, where your PMOS and MOS sizes were exactly the same, and it is 0.375 is the width and the length is 0.25. That's constant across both the analysis that we did. So in this case, W by L ratio of the NMOS is equal to W by L ratio of the PMOS, and that's equal to 1.5. Okay, and the next is the scenario where your Wn was kept to be same, 0.375, just as the previous experiment. Your Wp was 2.5 times of Wn, and your NMOS PMOS length, channel length, was kept to be same. So in this case, W by L ratio of PMOS was 1.5. In this case, we increase the W by L ratio 2.5 times of 1.5, which is 3.75. Okay, you can just do this divided by this and you will get this number. So it basically says your PMOS is bigger in size than NMOS. Okay, and each one of them has their own uses, has their own applications. I'll very soon tell you where this kind of waveforms or where this kind of buffers or inverters are used in a real circuit, in a real physical design circuit. So I'll come to that. So these two have their own applications. There is nothing called as good or bad. Everyone has got their own applications. So let's start with, let's look into the waveform. So this was the waveform, and this was the waveform for a device which was bigger than NMOS. So clearly, if you see, the shapes of the waveforms are same. If you see the shape of this one and the shape of this one, irrespective of the voltage levels at which they are switching, if you look into just the shape, they're almost the same. There are few glitches in this region and this region, and also over here as well, but the shape remains the same. So what does this tell us? This tells us that the CMOS inverter is a very robust device. Okay, there are certain parameters that will define the robustness of the CMOS, but this says that your CMOS, whenever your input is 0, this is your V in. Whenever your V in is 0, your output is high. Whenever your V in is high, your output is low. So this characteristics is being maintained across all kinds of CMOS inverter, across all sizes of CMOS inverter. So CMOS as a circuit itself is a very robust is a very robust device, and that's why CMOS logic is the one that is being widely used for any of the logic gate designing. Okay, so that brings us to the parameters that will define the robustness of the CMOS, and one of them is the switching threshold. Okay, For the first one is a switching threshold. Switching threshold means the point at which the device switches. So we are going to evaluate the static behavior of your CMOS, and we'll come up with some parameters like switching threshold, noise margin, and so on, that will define the robustness of your CMOS. So basically it will prove to us that CMOS inverter is the most widely logic used for building any of the logic gates, and why it is used. Because the characteristics of your CMOS inverter is such that it becomes very useful for these devices to be used in building of any of the logics. And one such parameter that will define the robustness of your CMOS inverter is the switching threshold. Okay, so let's find out what is switching threshold. Switching threshold is a point where your V in is equal to V out. Okay, so so basically, how do we derive it? We basically draw a line, a 45-degree line from this point till the end, and then identify the point at which your V in is equal to V out. Okay, so in this case, let's try to zoom in this one. If you look into this case, so this is the point where your PMOS is equal, your V in is equal to V out. Let's zoom in even more. Okay. So this is the point where your V in is equal to V out in this case, and this particular point tends to be somewhere around 0.9 volts. Okay. So it says that for this particular device, your switching threshold is a point where your V in is equal to V out, and that point lies somewhere at the intersection of this one and this one. So it lies somewhere over here. If you zoom more into this area, it will be about 0.9. Okay, that's with this kind of device where your WP is 0.375 and WP by LP is 1.5. And in the other case where you have another device, a bigger one, so in this case, if you zoom into this area, the point roughly comes to 1.25 something. It's not exactly at the center. If you see this one, this point comes to roughly about 1.2. This is the point where your V in is equal to V out. So that's basically an area at which you see the switching threshold to be somewhere where your V in is equal to V out. So this brings us to many conclusions over here. So this area that you see for your CMOS inverter is a very critical area, because your input is equal to output. That is first thing. Second thing, we have seen in the past that this is the area where your PMOS and NMOS both are in saturation region. Okay, it means both are kind of turned on. Okay, if both are turned on, there is a very high chances of leakage of leakage current. I'll talk about leakage current in a bit from now. So there is a high possibility that the current flows directly from power to ground. So in this area you see lot of current that is being flowing in this area. Since one of your devices is off, same thing with this area. In these two areas, since one of your devices are on or off, in this case your PMOS is off and NMOS is on. Sorry, your PMOS is on and NMOS is off. In this case, your NMOS is on and PMOS is off. In that case, there is no direct current that is flowing from your power to ground. Okay, but in this area, this is a very critical area where you see lot of power that is getting, a lot of current that gets flowed from power to ground. Okay, so this is a kind of short circuit device. Okay, I'll talk about these concepts in a bit from now. Let's move on and look into the switching threshold value. So these are the switching thresholds for this inverter and for this inverter, and the values we just identified. One in this case, it was close to 1 volt, so it's 0.98, and this case it was not exactly at the center, but it is about 1.2 volts. Okay, so these are the areas in which your PMOS and NMOS both are in saturation region. So we had looked into the waveform that while deriving this particular waveform, we had looked into each and every points of this one, at what regions of operation is your PMOS and NMOS are in. So in this case, we identified that your PMOS and NMOS are at saturation region. It means that they are kind of turned on in this area. Okay, and the reason they are turned on is because their gate voltage, I'll come to that point, the gate voltage almost crosses it. It's very much above the threshold region. Okay, so in this case, this is the case where your Vin is equal to V out. When you say Vin is equal to V out, your gate voltage is equal to your drain voltage, which means VGS is very greater than your threshold voltage. Okay, so this is the conditions. Your VGS is equal to VDS. Okay, and also another point is, at this particular point, at this particular operating region condition, the currents that is flowing in this area, that's almost same. Only the directions will be different, but the currents that flow. So for example, if there is a current flow from this area, from PMOS to NMOS, and from this capacitor to the NMOS, the direction of the currents are different, but the values of the currents will be exactly the same. Okay, that's why we write at this particular area your VGS is equal to VDS. Okay, and your current has got an inverse direction. Your IDSP, the drain current of your PMOS, will be in this direction, and the drain current of your NMOS will be in this direction. So if you note the directions of the current at this node, your PMOS current in this way and your NMOS currents in this way, so the direction of the currents are inverse. And as a result of that, you see your IDSP is your negative IDSN. So we have the boundary conditions, we have the conditions at which your switching threshold will arrive. So your IDSP is equal to negative IDSN, your VG is equal to VDS, and we also know what is IDSP, what is IDSN. So the next part is to next work is to derive the value of VM. So basically we need to solve certain equations so that we can get an early validation or early value of VM by just having the values of Wn by Ln or Wp by Lv. So it's basically we have these values and we need to calculate the VM, or vice versa. If we want to set a value of VM, what should be the value of Wn by Ln and Wp by Lv? So that's what we will be doing in the next video. So let's try to, since there are a lot of derivations involved and there will be a lot of analytical things that we'll be talking about, let's try to continue with the derivation of the switching threshold in the next video. Thank you. Hello everyone, let's continue our discussion with the switching threshold. So in the last video we came up with a task where we modified the PMOS sizes based on integer numbers of your NMOS and see what is the value of switching threshold. Okay, so basically we are trying to prove the robustness of switching threshold, and we'll try to plot switching threshold against how does the switching threshold varies with varying PMOS and NMOS sizes. Okay, so let's do that. So I have a SPICE simulator which is open over here. Okay, and we'll take the same circuit that we took in the past. So we have your PMOS which is 0.375, your NMOS is 0.375, and based on that values, our W by L ratio is 1.5. Okay, so this is what we are going to do. We have your dot DC as the same thing that we did in the past. Okay, so let's try to do a SPICE simulation. We have our SPICE simulator open. Okay, we will source the circuit file. Let me copy it out. Okay, we'll source it over here. .cir. Okay, we'll run the circuit. We'll set plot. The plot that is available to us is DC1. So let's do that. Okay, and let's see what are the plots which are available. So we'll plot out versus in. This is what we have done in the past, and this is the DC transfer characteristics of your CMOS inverter. So if you want to calculate the switching threshold, you just need to plot a line, a 45-degree line from the 0 point, and see where does that line intersects with this particular curve. It basically says that because whenever you draw a 45-degree line, its slope is 1, and whenever that particular point intersects for this particular curve, it basically says that is the point when your V in is equal to V out, and that's your switching threshold. Okay, so this was the DC transfer characteristics. In the meantime, what we'll do is we'll also try to do a delay calculation, a dynamic simulation of your CMOS inverter. The reason we are doing this is because this is the very good chance to identify what is the value of your rise and the fall delay of your CMOS inverter, and how does it vary with varying VMs. Okay, it's a very good point to start, and we'll be doing a whole course on dynamic simulation. So let's wait when we go over there. The dynamic simulation is a huge set of lectures, and we'll be covering it in a separate section of course. In this case, we'll just touch upon the dynamic simulation, where we identify what is the value of your rise and fall delay, and how does that vary with varying switching thresholds. Okay, so let's do that with the same configuration. We'll bring up one more spice deck. So this is how you do your dynamic simulation. Everything else remains the same, except the input that you provide will be a pulse. Okay, and your simulation command will be a transient. It's called a transient analysis. I'll come to the definition of transient analysis. So this is basically what it is called as. It's called the transient analysis, and the input that you will be providing, that is a pulse. A pulse is a waveform which is a function of time. So I'll show you what does a pulse mean. So what we'll do, let's try to show what a pulse means, or how does the definition of a pulse is being written into a spice deck. So if this is the pulse and if this is the spice deck, so this is what it means. If you have a pulse definition, it starts from 0. It starts from 0 volts. It ends to 2.5 volts. It ends to 2.5 volts over here. The shift is 0. So it says that your pulse is starting exactly at 0.0 at time unit 0. So if this would have been, let's say 50 picosecond, this pulse would have been started after 50 picosecond. Okay, so that's what a pulse means. You have a rise time of 10 picosecond, 10 picosecond. You have a fall time of 10 picoseconds. Okay, and the pulse width is 1 nanosecond, and this complete cycle is 2 nanosecond. So this is the complete cycle of 2 nanosecond, and if you just try to calculate the pulse width, which is a 50% duty cycle pulse width, it's 1 nanosecond. Okay, so this is what your pulse means, and we are going to supply this particular waveform as an input to your CMOS and do a transient analysis and see what do we get. Okay, so let's do that as well. So we'll again bring up our spice simulator. Okay, and now we have the netlist present over here, so let's copy it. Okay, so we'll source the circuit file .cir. Okay, now we'll run it and we'll set the plot. So you'll see a difference in the previous spice simulations and this one. In this case, the set plot will tell you it's a transient analysis. Okay, it basically says that we are doing a transient analysis. In the previous case, since we did a DC transfer characteristics, it basically says it's a DC one or DC transfer characteristics. In this case, we are doing a transient analysis, so it's called tran2. So we'll put tran2. Okay, and let's see what are the plots available to us. So we need to plot the input as well as the output waveform to calculate the delay. When you calculate the delay, it's basically 50% from it's basically a point at which your input crosses 50% to a point where your output crosses 50%. Let me show you that. So we'll plot out versus time, okay, and the input waveform. So this is what I meant. So it's not clearly visible. I'll make it visible. So this is your input, and this is how your output switches. Okay, so if you want to calculate the rise, let's say we are going to calculate the rise delay. So this is your rise, this is your point when your output voltage rises, and you need to go to 50% of this particular waveform. So 50% is 1.25 volts. Okay, we'll zoom in. This is the 1.25 volts. We'll zoom in even more. Okay, and once you get that, you just need to click on this one. So this is your time axis, which is in nanosecond. This is your voltage axis. So if you want to calculate the delay, you just need to identify the difference between this point and this point. So this is your rise waveform. It's a zoomed in version of your rise waveform. This is the falling edge of your input waveform. So if you just click on this one, if you click on this one, or basically this is the way the spice simulator works, you just need to identify what is this point from the time point of view. You need to identify what is this point from a time point of view to calculate the difference, and that there you will get the rise delay. So let's do that. We'll click on this one. So this is basically 1.0144 on your X, 1.0144 nanosecond. 10 raised to minus 9 is nanosecond. At y0 is equal to 1.25 or approximately equal to 1.25. Okay, so this is 1 point. We'll click on the other one, and you'll get the other point 1.16277, and then take the difference between this one, and this will give you a rise delay. So let's do that. So we'll clear this 1.16277 minus 1.01446. So 0.14 or 148 picosecond is your delay. So that's your rise delay. We'll do the same thing for fall delay as well. Let's close this ones. For the fall delay, you need to find out a point at which your output falls. In this case, the output falls at this point. Okay, and this is when your input is rising, and we'll need to take the 1.25, the 50% of your input voltage waveform, and let's see what do you get as the fall delay. We'll zoom in 1.25. We'll zoom in even more. Okay, we'll zoom in even more, and let's see what do we get. And we'll follow the same strategy. We'll click on 1.25 at over here. So your x0 or the x-axis shows as 2.00486 nanosecond. Okay, same thing. We'll click over here. We'll get 2.07653 nanosecond, and then calculate the difference between it. So we have our calculator. We'll take 2.07653, okay, minus 2.00486, and this comes to about 71 picoseconds or 0.01 nanosecond. So this was about how do you calculate the rise and the fall delay for the inverter, and let me jot it down. So for a value of WL by WP, WP by LP equal to WN by LN, this is the rise delay and the fall delay that we just calculated. It's 148 picosecond is the rise delay, and the fall delay is 71 picosecond. And you draw a line, you draw a 45-degree line from 0 as 0, and this is the point at which it intersects. Okay, and if you zoom in over here, so let's zoom in over here. The quick way to do is click on this line and just zoom in. So if you zoom in over here, if you see, this particular is the point where this curve is intersecting with the 45-degree curve, and that particular curve is somewhere at 0.9. It's somewhere lying at 0.99 volts. So your switching threshold is equal to 0.99 volts. Your rise delay is 148 picosecond. Your fall delay is 71 picosecond. Okay. Similarly, what we'll be doing is we'll be doing the same thing for all this set of combinations. I know it's a tedious work, but we need to do it, and we'll plot a table specifying what is the value of your switching threshold, what is the value of your rise and fall delay, and eventually deduce a conclusion about the CMOS inverter robustness. So let's try to do all this in the next video. Thank you.
PDKs, Sky 130. What's inside this? Yeah, it's inside the text file, and it's inside magic. Yeah, if you do an ls minus LTR, yeah, this is the text file we're talking about. So we'll copy this. Make sure you do a copy, CP, and our location was this. Okay, so this is basically copying this sky138.tex file from this location, that is the libs.tex/magic, to the directory which we had just cloned right now. So that is done. Just verify if that's copied or not. Yes, it's here now. So you can basically type the entire absolute path, and then just like how we did for during the floor plan in the placement stage, where we want to see the layout, we do magic -t, we write the entire absolute location to the text file, then we do left and that entire path. So this is a simpler, you copy it first, it's a one-time job. We will just close this because we don't have, okay, we will be working on this. Clear the screen, do ls-ltr. Okay, so this command we have used earlier when we were seeing the layout for the floor plan the placement state, you do magic minus T for technology. Our technology file is what we copied right now. Since it is there in this folder itself, you don't have to give the entire absolute location. And then we need to the mag file. This is the mag file. That's it. This ampersand is used to free the next command prompt. If you don't use the ampersand, this magic will keep the next prompt busy, so it won't free up the prompt. See, in the background you can see it has freed up the prompt. So this is my inverter. Just like layout, we'll first place our cursor somewhere else. We'll do an S. We will do a V. It has been centralized.
Hello everyone. Let's begin with the 16 mask process, and the first step towards that is selecting a substrate. Now substrate is something on which you fabricate your complete design. So basically we do a physical design step, we do all those kind of steps, and finally the GDS2 or the layout that you see on your physical design step or any step that gets actually fabricated onto a substrate. So the first step is to select a substrate. Normally we will go for there are various kinds of substrates that are available, but we'll go for the most common one which we use for most of your mobile devices or any kind of devices that you see or any kind of chips that you see in the real time. So we'll go for a p-type silicon substrate. It will have some different properties, and some of them are high resistivity or the resistivity property of the substrate. The doping level. Doping is the process of adding a foreign impurity into a p-type substrate. So something which comes as a foreign material, it's called as doping. That's why the name doping has been put over here. The doping level of this particular substrate is maintained to be 10 to the power 15 per centimeter cube, and the orientation of this particular silicon substrate is 100. We'll talk about orientation in a separate course, in a separate set. In this case, just focus on the kind of substrate that we have, the resistivity and the doping level. And the reason for having this kind of doping level is that we have to maintain a doping level which is less than the well doping. So when we talk about well doping, wells are nothing but something which we'll be creating over here to fabricate your PMOS and NMOS separately. I'll come to that in a bit from now. It is coming in the further sections. So the doping level is maintained low so that it is lower than the well doping, and the well doping are the ones which you will be using to fabricate your PMOS and NMOS. I'll come to that in a bit from now. Okay, so we have selected a substrate. It's called a p-type substrate. The next step is to create the active region for transistors. So when we talk about active region, these are the places where you actually see your PMOS and NMOS. So on your p-type substrate, we are going to create some small buckets or some small pockets which will be called as active region, and in those pockets we are going to create the PMOS and the NMOS transistor. Okay, so those pockets will be connected, and the connections to those pockets will be brought about in the higher metal layers. But the first step is to create those buckets or create those pockets. So let's try to do that. Those are called as the active region for transistors. So the first step to do that is to create an isolation between those pockets. So because the pockets within itself or the active region or the active transistors onto the p-type substrate should not interfere with each other's working. So that's the goal, and the first step towards that is to create isolation between each and every pockets. So let's see how do we do that. The first step is to grow a silicon or silicon dioxide. It acts as an insulator. It acts a very good insulator. So we grow a 40 nanometer of silicon dioxide on your p-type substrate. That's the first step. Okay, the next step is to deposit a layer of silicon nitride. It's about 80 nanometers. So the reason we are depositing Si3N4 or the silicon nitride onto a silicon dioxide will be very much evident in the upcoming video. So let's stick to that. So we'll deposit an 80 nanometer layer of silicon nitride onto the 40 nanometer layer of silicon dioxide. And now is the step where we have to create the pockets. Now the first step to create the pockets is to identify the regions where we have to create the pockets. So the first step is to deposit a layer of photoresist. So I'll come to the word resist. So when we say photoresist is something as a film. It's a negative or a positive film that you see for a camera. Let's say when you in the older generations camera, you had a positive film and a negative film. So the concept of that camera can also be applied onto a photoresist. So photoresist is a film on which we are going to do some process that will clearly define some regions over here. I'll come to that in a bit from now. So let's see how do we do it. So the first step is to deposit 1 micron of photoresist. Okay, and this is the one on which you will create some mask. So your mask one is nothing but, now we are talking about layout. So when we talk about layouts, those are nothing but called as masks in a fabrication term. So when we talk about polysilicon layout or any kind of layout that you see in your custom design, those are converted to mask, and this is the mask. It is the first mask that will be picking up from that particular area. So let's look into the mask one. So it will look something like this. This is from your top level, the layout looks a bit different. This is the cross-sectional view of your mask or of your layout. It is nothing but a protection layer. So for example, now I decide to create my well region only in this area and in this area. So I have to protect this area from getting exposed to anything else. I have to protect this particular area, and also I have to protect this area. Now, how do I do that? The way to do this is using photolithography. So the photoresist that you see over here, that is now being part of the photoresist is being now protected by something called as mask. So when the ultraviolet light hits the photoresist, it doesn't hit this area. Okay, it doesn't hit this area, but the only area that the ultraviolet light will be hitting will be this area and this area and this one. So these are the regions that are getting exposed to your ultraviolet light, and hence there will be some chemical reaction that will be happening for this area and this area, but there will be no chemical reaction for the area which is underneath your mask. Okay, so these areas are getting protected, these areas are exposed to the UV light, and while these areas are exposed to the UV light, we do some chemical combination. We basically wash this extra resist off from this region and this region and this region, and we get patterns something like this. Okay, so the extra resist that was exposed to the UV light is now getting washed away. So you have now a protected area over here on which you can do some process, or basically you can protect this area from the further processes that I will be showing now. Okay, so the next step is to remove the mask. So now when we remove the mask, now there is an area which is this small area, and this small area, under which if you do certain kind of chemical actions, or if you do some kind of deposition or something, or etching something, it will affect only the exposed area and not the ones which are underneath the photoresist. So it's a protection layer for you. Okay, and that's very common, and that's the reason we have all this custom layout and everything layout that we are going to discuss. This is just an example of how does the layout actually helps you to do a photolithography process while you try to fabricate your chip onto a silicon substrate. So so moving on, what we'll do is we'll now create patterns. First of all, we'll etch off the silicon nitride. Now since we have the photoresist present over here, only the area underneath the photoresist will be protected, and the remaining area will be etched off. The silicon nitride is being etched off from the other areas. The next step is to remove the photoresist itself, because the silicon nitride itself will act as a very good protection layer to grow the oxides on the other areas. Okay, now I will now show you how do you grow this particular, how do you grow the oxide and the remaining area, and that will eventually act as an isolation layer. But the point over here is the silicon dioxide area which is being under silicon nitride is protected from growing more. Okay, similarly for this area and the other areas, when we put this particular thing into a furnace, into a very high temperature furnace, the other areas of the silicon dioxide will grow, while the areas which is under the silicon nitride is getting protected. So let's see how does it look like. We'll put this particular complete thing in an oxidation furnace. So a furnace is a place which works at very high temperature, like up to 900 to 1000 degrees Celsius, and we will that actually helps to grow the oxide in the other areas. So we have grown the first level of silicon dioxide in an oxidation furnace itself. Now there is a second level of growth of oxidation, so we'll do that now, and it will look something like this. So if you see over here how the silicon nitride has actually protected the areas underneath to grow, while it was not able to protect the area which were at the edges because the growth is so strong. But it has clearly protected the area which is maximum, almost 90 to 95% of the region underneath has been protected from the silicon dioxide growth, while the silicon dioxide has been grown in this area, and this area. Okay, and these are basically nothing called as isolation region. Any transistor that will be fabricating over here, they will lie in this area and this area. So these two transistors will now not communicate with each other, because you have isolation, clearly defined isolation area which is made over here. And this process that we have done is referred to as low cost. So this is called as field oxide, and the process is referred to as low cost. Low cost is nothing but called as local oxidation of silicon. Okay, so the process is referred to as local oxidation of silicon, and this area is referred to as bird's beak. So this is how you protect your two different transistors from communicating with each other. The next step is to remove the silicon nitride, or the etch out the silicon nitride, or strip it out in a hot phosphoric acid. Okay, so this is how you get your isolation region. So this areas and this one are your active region, where you actually grow your transistors, and the isolation region will protect this transistor not being communicating with this transistor. So you have actually created an electrical isolation over here. Okay, so what we'll do is we'll stop at this point. The next step is to create the N-well and P-well. So N-well is the place where we are going to build your PMOS, and P-well is the place we are going to build your NMOS. So let's try to look into all this in the next video. Thank you. Hello everyone, let's continue with the N-well and the P-well formation. So the next step is again to protect one of the areas. So as we said that N-well will be used for PMOS fabrication and P-well will be used for NMOS fabrication. Both can't be done at the same time. We need to protect one layer while we need to protect one area while we fabricate the other. So let's try to see how do we do that. So the same steps arrive over here. You deposit a layer of photoresist, and then you define patterns which layer you have to protect. For example, in this case we'll use the mask 2. The next mask 2 will try to protect this area. So now in the past video we have talked about how does this mask 2 looks into a layout. So if you look into a general layout, so let's say if you look into a top view of a layout, this is a CMOS inverter layout which I have drawn in Magic. So if you look into this particular layout, the mask 2 will generally refer to this one. So what you see as a top view of your mask 2 is nothing but this is the cross-sectional view of your mask 2. So now it is very easy to relate the layout with your mask. So this is how the fabrication team and the layout team communicate with each other. So there are certain files that they exchange between each other, but this is how it looks like. If this is your top view for your mask 2 for your active area, this will be the cross-sectional view of your mask in the active area. Okay, so now we have this mask 2. The next step is to expose this photoresist to an UV light. So the same thing happens. The light doesn't react with the resist which is under this area. It only reacts with the area which is exposed. And then once you wash away this particular thing into a solution, this particular area of your photoresist gets washed away. Okay, so now this area is available for any chemical reactions or anything that we have to do over here. So the next step is to remove the mask itself, and finally you have to create a P-well over here. So the P-well is done using a boron. Boron is a P-type material. Okay, we are not discussing the details of boron itself as an atom or an ion. Just take it from me that the boron is a P-type material, and it is diffused into this particular P-type substrate using a process called as ion implantation. So boron being a P-type, it creates a P-well over here, and the energy that is needed to diffuse the boron through the oxide layer present over here, it's about 200 kilo electron volts. We'll talk about the energy and the ion implantation process in a separate course. In this set, just take it from me that ion implantation is a process like there are some ions that is getting shot inside this particular area with a very high energy. Okay, so boron is a P-type material which needs a high energy because it has to pass through this particular thin oxide and then enter into the P-type substrate. So the amount of energy, a bit of higher energy is needed over here. It's about 200 kilo electron volts, and the boron it penetrates through the oxide layer and it enters into this particular active area, into this particular P substrate, creating an active area P-well over here. Now, while boron penetrates through the oxide layer, it does damage this particular oxide layer. So we'll talk how do we repair the damaged oxide layer. We'll come to that in upcoming videos. For now, we'll just deposit, or we'll just ion implant the boron, which is the positive type material, into the substrate using ion implantation with a high energy of 200 kilo electron volts. Okay, so we'll do a similar step for the N-well as well. You deposit, so I have just cut down some process steps over here. You deposit the full resist, you create a mask over here, you expose it to the UV light. This section of your resist gets exposed to the UV light and hence can get easily washed away. Okay, so I've just cut down those steps just to save time in this case, and just to save repetition of steps. So in this case, now this particular area is being exposed to any kind of reactions or process that we need to do. So in order to create an N-well process, or in order to create an N-well, we need to use a phosphorus as a material. So phosphorus is an N-type material, and it's a bit heavier than boron. So ion implantation is again the same process. We use same ion implantation process to implant phosphorus, that it penetrates through the oxide layer and creates a N-well over here. Okay, the energy of this particular phosphorus, the ion implantation energy for depositing or for implanting the phosphorus atoms is a bit high, because the phosphorus atoms are heavier than your boron atoms. Okay, so next it creates an N-well over here, and once it creates the let's name it over here. So it creates an N-well over here. So we have created the wells over here, but the depth of the wells are not finalized yet. So these are just the well creation. Next we have to diffuse the well so that it occupies almost half of the substrate area, so that we have clear room available for the PMOS and NMOS fabrication. Okay, so the next step is to take this complete substrate into using this particular structure into a high temperature furnace. It is called as a drive-in furnace. Okay, so the next step is to take this into a drive-in furnace, push it to a very high temperature for a very long time, let's say about 1100 degrees Celsius for 4 to 6 hours, and that will drive in the boron or diffuse the boron and the phosphorus atoms into the p-type substrate, forming clear wells over here. So these are called as twin tub process. Okay, so why it is called twin tub? So we can consider this as one of the tubs, and this is the another tub. So there are twin tubs in which, in this particular N-well, we are going to create an PMOS transistor. In the P-well, we are going to create an NMOS transistor. So this is the first step towards creating the pockets that we were talking about in the previous lecture. Okay, so now that we have created the P-well and the N-well, the next step is to create the gate. The first step that we are going to do is create a gate. So we have learned about transistors in a separate videos, where we talked about transistors consist of source, drain, and gate. And so the next step will be to create two different gates for the PMOS and the NMOS, and we'll look into the fabrication steps for that. So let's try to look into all that in the next video. Thank you. Hello everyone, let's continue our discussion with formation of gate. So gate by far is the most important terminal of your NMOS or PMOS transistor, because that's where you actually control your threshold voltage, and threshold voltage is nothing but the turning on voltage of your transistor. So that's maintaining that voltage is really very important, and as a result of that, the fabrication of gate terminals becomes really very important over here. So let's look into that. But before jumping into the fabrication steps, we had looked into let's look into one of the snippet from one of my course called Circuit Design and Spice Simulation. In that course, we had talked about the threshold voltage equation over here. Okay, and the threshold voltage was very much dependent upon the body effect coefficient, which was gamma, and gamma is factored by the doping concentration Na and the oxide capacitance. So in turn, if you control the doping concentration and the oxide capacitance over here, that will impact your threshold voltage. So the way things are done is, in our fabrication steps, you try to maintain a doping voltage and an oxide capacitance in such a fashion that you get your required threshold voltage for the transistors, and these are all fabrication steps. Okay, so that's what are really very important to control over here, because these are quite controlled experiments that we are trying to do over here. So now you see how does the fabrication are closely related to your threshold voltage, and threshold voltage decides the turn on voltage of your gates, which in turn decides the functioning of the gate. So these are all interrelated. Okay, so let's try to look into how do we do that. So we are going to control the oxide capacitance and the doping concentration through the further steps. So the next step for the formation of GET is to maintain the doping concentration. So let's see how do we do that. So for example, you have a P well already over here where we are trying to fabricate the NMOS transistor. So we'll use another mask 4. So this is a 16 mask process, out of which we are now completing the 4th mask. So the 4th mask, the steps remains the same. You actually spin photoresist on the complete surface area, then you protect one of the area by a mask 4. You give ultraviolet light, you expose this to ultraviolet light. This section of your photoresist gets again exposed to the ultraviolet light, and hence there is some chemical action that happens on this resist, and this resist gets washed away. Okay, these steps are the repetitive steps that we have to do every time we are trying to do a photolithography, or every time we are trying to introduce a mask or a layout. Okay, so with that said, you have this area exposed for any further process steps that we need to do. So what we'll do, we'll introduce boron over here. Boron is again a p-type material and with a low energy. So energy that we had used for the formation of p well was something higher than this one, because we wanted the boron to penetrate through the thin oxide right into the substrate. But in this case, we want the boron to be just at the surface. And as a result of that, we are using a low energy for this particular boron implant, and we'll use the dose. The dose of the boron will be maintained in such a fashion that we attain the required doping concentration over here. And that doping concentration value is dependent on the threshold voltage that we just saw a couple of minutes back. Okay, so that's how you modify your doping concentration over here, and as a result of that, your threshold voltage comes under control. Similarly, we have to do the same thing for your NMOS also, but for your PMOS also. But one thing to be kept in mind, again, the boron is getting doped from this area. It penetrates through the oxide and enters into the P well. So there are some damages that happens to the oxide, and I'll come back in a minute. How do we control, or how do we maintain these damages, or how do we remove these damages? Okay, so I'll come to that in a minute. So next is the mask 5. We have to use the mask 5 and repeat the same steps for the PMOS that we are trying to fabricate over here. Okay, we also need to control the threshold voltage of your PMOS, and we do the same thing, the spinning of the resist, mask, ultraviolet light, some chemical reaction, and then this particular part of your resist gets washed away. And now this portion is again exposed to any n-type impurity. We can use phosphorus, or we can use arsenic. Arsenic is again an n-type impurity, so it doesn't matter. Okay, and we'll use the energy as low as to maintain the arsenic doping just to this level, and this in turn will help you to control the threshold voltage of your PMOS as well. Okay, so that's about the threshold voltage. Next, we have to fix the oxide. So what we'll do, this oxide is already there are a lot of damages because of the implantation steps that we have done. So what we'll do, we'll remove this particular oxide using hydrofluoric acid. Hydrofluoric acid reacts with the SiO2 to remove the oxide portion of it. So there is some chemical reaction that happens, which I am not getting into, but hydrofluoric acid can be used to strip off or etch off the oxide, extra oxide that you see over here on above the P well and the N well. Okay, and once you do that, you regrow new oxide, high quality oxide of the same thickness, roughly about 10 nanometers thin, or again on the P well and the N well. So this can be controlled based on the threshold voltage that you need. So we just saw the oxide capacitance and the doping concentration. Doping concentration was maintained by the p-type and the n-type impurity implants that we did in the previous steps, and again the oxide capacitance is now controlled by the oxide thickness, which is maintained over here. Okay, so 2 parts has been taken care, and now the final step where we have to look into the gate formation over here. So the steps are pretty simple. You deposit a polysilicon layer using some of your deposition techniques, and grow a thick polysilicon layer over here, roughly about 0.4 micron or 400 nanometers. Okay, and the gate area is supposed to be low resistance. So what we do is we dope it with some more impurities. So if we take any of the n-type impurities like phosphorus and arsenic and implant it on the complete on the complete polysilicon layer to have a low sheet resistance, and as a result of that, the low gate resistance. Next steps are very simple. So basically you take again, you again deposit a photoresist over here. You use the mask 6 as the gate mask, as a gate or a polysilicon mask. So something about the mask 6, if you had looked into my previous previous one of the snippets that I had shown in the previous couple of lectures for the layout of your CMOS inverter, this is what your mask 6 will look like. So mask 6 is a polysilicon mask. So these are your gate areas. Only that the difference that you see is if this had been tilted towards the right side, you would have seen exactly what the mask will look something like this. So if you look into the top view, it is like a square shape over here. But in this case, we have used a mask which is something like this. We have not made a right angle over here for some reasons which we'll talk about when we go into the layout section of it. But this is the gate mask, and this is the top view of the gate mask that we are using just now. Okay, so this is the gate mask, and this is mask 6, which is the cross-sectional view of the gate mask. You again remove this mask, you etch away the extra resist that is present over here because of the UV light exposure. Okay, now this portion can be this mask can be removed, and the remaining areas from the polysilicon, the remaining areas which are outside the photoresist, can be etched away. Okay, in that way you get your polysilicon gate. And now the final step is to remove the resist which is present over here, and this is what you get as a gate. Okay, so now this complete procedure is a complete controlled procedure. In this case, you have actually controlled your gate voltage using your doping, using your oxide capacitances, and also made a low resistance gate by additional doping of polysilicon with n-type impurity like phosphorus and arsenic. Okay, so what we'll do is that this is the step of formation of gate. The next step is to open a lightly doped drain formation. So this is again an important concept. We need certain structures of your source and drain in such a fashion which will give you the highest performance. So let's try to look into the next step, which is LDD formation, from the next video. Thank you. Hello everyone, let's continue our discussion with the LDD or the lightly doped drain formation. So what we want to exactly achieve over here is this doping profile. So if you see over here, the doping profile over here we try to attain is P plus P minus N. So what do you mean by this? This is your N well where we are trying to fabricate the PMOS. So in case of a PMOS, you have source and drain, and source and drain are both P type. Okay, so that's this one P plus, that is the P plus doping profile which is coming over here. P minus is the lightly doped drain formation or the LDD that we are trying to bring up now, and N is what you already have. So this is the kind of profile or the source drain profile that we're trying to see over here. Okay, similarly for your PMOS, for your NMOS which is being fabricated in the P well, you need the N plus will be the source and drain. So your source and drain for your NMOS are all N type. So N plus will be the source and drain doping. N minus is the one that we are going to form now, the LDD formation over here, and P is what you already see. Okay, so this is the kind of doping profile that we are trying to attain over here. Now the question is, why do we want this kind of doping profile? Why not P plus and N or N plus and P? Why do we need this P minus and N minus over here? So there are two reasons for it. So let me try to brief out the two reasons over here. The first reason is the hot electron effect, and the second is short channel effect. So these are more of a device physics thing, but let me try to brief you about this kind of effects. So about the hot electron effect, when the device size actually reduces, okay, what the general practice is to not change or not redesign the power supply. So in that case, your electric field, so if let's consider this electric field formula, it's E equal to V by D. So when your device size reduces, D reduces, your electric field increases. Okay, and as a result of that, there are various effects that happen. The first of the effects is that there are the high energy carriers, there are the energy of the electrons and the holes attain a tremendous amount of energy. And this energy carriers can break your Si-Si bonds, leading to some more additional electron and holes, which we don't want because we have controlled the doping profile very well. Okay, and the second reason is the energies might be so high that it crosses the 3.2 electron volts barrier between the Si conduction band and the SiO2 bands. So this is the general general energy that holds on, that is basically maintained between the conduction bands, and if it crosses this band, it might just enter into the oxide layer which is just present above your substrate, and it might create reliability issues. So this is the hot electron effect. Okay, the next is the short channel effect. So basically when your device size reduces, for short channels, basically when you move from 1 micron to 1 micron gate length to 0.5 micron gate length, the drain field, the drain area or the drain voltage just penetrates into your gate, just penetrates into the channel area. Thus it becomes very difficult for the gate to control the current, the source and the drain current. So these are the effects that we will be covering in detail in the device physics course. Let's not get into more details of that, but we'll try to control these two effects in the fabrication process. Okay, so let's try to look into the process that we will be doing to generate the LDD structure. The process remains simple. It's pretty simple what we did in the past, and in this case the gates that we have formed over here also helps us to create this particular area open up for the further process that we want to do. Okay, so it goes something like this. So you create a mask. You basically, again, this is mask 7. You spin a photoresist over here. You create a mask of a mask 7. It is called mask 7. You protect this area. UV light is getting directed over here, and the UV light reacts with the photoresist, and the photoresist reacts with there is a chemical reaction that happens in the photoresist, and it gets forced away. So the standard steps for photolithography still remains the same. It holds good for whatever steps we do. Okay, and the next step is to now in the case of a in case of P well, we are trying to fabricate the NMOS over here. So we need an N-type impurity, which is phosphorus. So we have seen in the past phosphorus and arsenic as the N-type impurity. Okay, so we are trying to use the phosphorus, or we can use some other N-type like arsenic, but in this case we'll use a phosphorus N-type impurity and try to do an implantation over here. Okay, it will look something like this. It will be the doses and the energy of phosphorus is carefully chosen so that the N minus implant doesn't penetrate well into the well, or it doesn't penetrate very much into the well. It just stays over here. So the dose are being very much maintained to create an N minus doping concentration. N plus generally means heavy concentration. N minus generally means lightly. That's why it's called lightly doped drain. This becomes a lightly doped. Okay, so this is your N minus implant, and this particular gate protects the phosphorus from entering into this channel area. So next is basically, again, we do the same thing. We apply a photoresist and do the photolithography step, and we create this mask 8. So this is a 16 mask process, out of which now we are covering the mask 8. So the next step is again to protect this particular area from further implantation and expose of this area for a P-type implant. So boron is again a P-type implant. The doses are again carefully chosen in such a fashion that it creates a P minus implant over here. And these are all lightly doped. So what you see over here are too much lightly doped. So we are not done with this one, because we have to somehow maintain the further source and drain. When we try to generate the actual source and drain, it might get entered into this one, or this structure might just get disrupted. So we have to protect this lightly doped drain structure. So how do we do that? We create some spacers over here. Okay, we try to create some sidewall spacers, and this is how do we do it. So what we'll do is, let me try to first create the spacer over here, and then I'll try to explain how does it protects from the further source and drain formation. So we'll deposit a thick SiO2 or Si3N4 layer on the complete structure. We'll do some anisotropic etching. So anisotropic plasma etching is more of a directional etching. So what it will do, it will try to etch each and everything over here, but it will but the oxide which is present at the side walls will remain over here, because that's the way the anisotropic etching works. Had it been isotropic etching, it had removed all the oxide from each and every corner of your structure. But in this case, for the anisotropic etching, we'll talk more about anisotropic etching in a separate course. So this helps us to prevent this particular oxide layer from getting etched away, and these are called as sidewall spaces. So now how does this sidewall spaces actually help us? So when we look into the further in the further videos where we are trying to create the source and drain, the source and drain implementation will be affected only in this area, and hence this particular portion of your lightly doped drain is kept intact. Similarly, when we try to do an N plus implantation over here, the N plus implant will be only in this area and this area, and the side wall spaces help to maintain the N minus implant over here. And hence we get the N plus, N minus, and P doping profile that we expect. So what we'll do is we'll stop at this point, and in the next video we'll look into how does the source and drain formation happen. So let's try to look into all this in the next video. Thank you. Hello everyone, let's continue our discussion with the source and the drain formation. So the next step is to add a thin layer of screen oxide over here. So if you see over here, I just added a small thin layer of screen oxide, and the reason to that is to avoid the effect of channeling. So channeling is an effect where when you do a lot of ion implantation, if the vector velocity of our ions matches with that of the crystalline structure of your p-type substrate, the ions might go deep inside the p-type substrate without even hitting any of the silicon atoms. Okay, so in that case it might just fill up this entire of the p-type substrate without even getting blocked at this point. So by adding a thin amount of screen oxide, we try to randomize the direction of the ions. Okay, so that's the purpose. We'll talk a lot about channeling effects when we go further in this video. So a thin screen oxide is added to avoid channeling during implants. Okay, it will just help to randomize the direction of the implantation, and they will try to settle down in the areas that we want them to settle. Okay, so the next step is to use the mask 9 now. The process is still the same. The photoresist is being spun on this particular structure. It is being opened to ultraviolet light, and there is some chemical reaction, and this photoresist gets washed away. So this portion of your p-type substrate or of your structure is being now open to other implants. Will now remove the mask which is present over here, and will expose this structure to arsenic. So there are two types of negative or N-type impurities that we have been talking about. It's arsenic and phosphorus. Let's try to go with arsenic in this point. Okay, so the amount of energy that will be needed is 75 kilo electron volts, and this will just go right inside over here, and the side walls over here, which are actually the side wall spaces, and the reason that we have added the side wall spaces is to have the LDD being intact. Okay, so I'll show you what happens when you have a side wall spaces. So in this case, so arsenic will try to deposit only in this area and this area. So this is what happens. So now you see the structure over here, the LDD, the lightly doped drains are still maintained. There is some amount of N minus implants present. Now these are the N plus implants that we just did using arsenic. So in this case, we have got a source which is N plus, we have got an LDD which is N minus, and we have a P-type area over here. This is the kind of structure that we actually needed, and we have discussed in the past video. Okay, so similarly we'll do for the next thing also. We'll try to, this is called the N plus implant, and now we'll do the same thing for the P-type also, for the PMOS as well. So we'll have a mask 10 now. So we are closing to 16 masks. So this is the mask 10. The same process, resist is being spun, it's being exposed to UV light and so on, and then in this area is now exposed to any kind of implants. So we will now use the boron. So boron is again a P-type impurity, and it is being a lighter than arsenic, so the energy is being less that is being used for arsenic. Arsenic we use about 75 kilo electron volts, and boron we are using 50 kilo electron volts. And in this case now the boron does the same thing. It gets entered into this particular open area. So this is the open area for boron. It will go here and settle down in this area. And this is now the P plus implant. So this is a similar structure that we needed for your PMOS. We wanted a P plus, P minus, and an N kind of structure in this case. Okay, so this is your PMOS, this is your NMOS, and we'll try to remove the mask and put this particular MOSFET, the half-built MOSFET, into a high temperature annealing. We'll put them into a high temperature furnace. Furnace could be about 1000 degrees Celsius, and we'll expose this to high temperature annealing. So annealing is a process. It is very similar to what we did for the P wells and the N wells, like the drive-in diffusion. It will force or push this particular N plus and the P plus and the N plus impurities into the even more into the P-type substrate. So this is how your temperature, this is how your source and drain will look like. It will penetrate more into the N well. Okay, the N plus will penetrate more into the P well, and this is your source and drain for your PMOS. This becomes a source and drain for your NMOS. and this process is referred to as high temperature annealing. So what we'll do is we'll stop at this point. The next video onwards, we have to look into the steps to form the contacts and interconnect. So we have the gate, we have source and drain, and similarly for your NMOS also we have the same. The next step is to create the interconnects or the metal contacts. Okay, so let's try to come up with the metal contact thing in the next video. Thank you. Well everyone, let's continue our discussion on building the contacts. So contacts are really very important because that's the only thing that is accessible for an user and through which you can control the electrical characteristics of your PMOS and NMOS. So that's the only thing that is available for us. So let's try to build up contacts. So the first step is to remove the thin screen oxide that we had deposited. So remember, sometime back in the previous video we had deposited the screen oxide just to avoid the channeling effect. So it's time to remove them and open up the contacts, open up the source, drain and gate region for building up the contacts. So let's etch that off. So we will remove this using an hydrofluoric acid solution. So it's a solution that reacts with your oxide and etches it off isotropically. So let's try to do that. And now we have etched off your surface. Now this surface, the gate and the source and drain, this gate and source and drain are now open for any type of contact building that we want to do. Okay, so let's start with the local interconnect. So there are the various steps to do it. The first step is to deposit a titanium. So titanium is a metal which is got very high connectivity or very low resistivity. So we'll use titanium as a metal for now, and the way we are going to deposit titanium is through sputtering. Now let me try to give you a brief idea on what sputtering is. So sputtering is basically you take a titanium metal over here, okay, you place a titanium metal and then you hit the titanium metal with some argon gases. Okay, so what happens when you do that? The titanium metals, the particles of the titanium metals will get sputtered out, will get removed from the titanium, and it will get deposited onto the substrate. And these are all very controlled experiments that we do. Okay, so titanium metal, the metals which are there outside on the surface of titanium, they are being hit by the argon gas and they emit out titanium metals and they get deposited on the substrate. So this process is called as sputtering. We'll talk details about sputtering in a separate course. So let's understand the basic behavior. How does physical sputtering behave? So this is the way we'll deposit titanium. So the way and the titanium will be deposited all over this structure. So it will look something like this. Okay, so in this way the titanium has got deposited all over them. We know that the titanium is a metal. The next step is to create a reaction or create a contact between this titanium metal that we have deposited and the source, drain and the gate regions. So the best way to do is to put it in or heat it in a nitrogen ambient, and the result for that and the heating is being done at a very high temperature. It's about 650 to 700 degrees Celsius. So when we do this with a nitrogen as an ambient, there are some chemical reaction happens, and the result is you will get some titanium silicon dioxide, TiSi2 material, which is this one. These are low resistant contacts. So now if you see the poly contacts and the contacts which is present over here, they're all being made now. Okay, so let me take you to the previous figure. Previously it was like this. Okay, so now this titanium over here, the titanium over here, whichever are the ones which are in contact with the silicon, they react with silicon to form titanium silicon dioxide. So TiSi2 is a low resistant metal which can be used for your local interconnects. And not only that, there is another chemical reaction that happens between titanium and the nitride and the nitrogen ambient, which is TiN. It's called titanium nitride, and that is used only for local communication. Because of the kind of resistivity that it has, it can be used only for your local communication. So now you have two kinds of metal contacts over here. You have this contacts, which is titanium Si2, TiSi2 over here, and also for your NMOS you have 3 titanium Si2, and there is another TiN available which is deposited on top of each and every structure. So the next step is the deciding factor, which all are the contacts that you want to bring to the next level, because there are some contacts which can be connected internally. So for example, if you look into a CMOS structure, the drain part of your CMOS, the NMOS and the drain of your NMOS and the PMOS are tied to the output. Okay, so that can be locally connected, but the output can be taken off through some higher metal level connections. Similarly, you have to decide on which kind of connections can be done locally, and those connections are done using the titanium TiSi2 TiSi2 that you have over here. And for the connections that you want to bring at the top, you can use the next level of metal, which is TiN. Okay, this level of contact can be used to bring up the bottom connections right to the top. So let's try to do that. What we'll do, we'll use the same process. We have our mask 11 now. So we have done till mask 10, and now this is mask 11, and there are 5 more masks to go. Okay, so we have the same mask, the same process. We deposit resist, we spin resist. Basically, we spin the resist on the structure. We expose it to UV light. Chemical reaction happens, and the resist gets washed away. So this is the structure that we are actually looking forward. So now what we want is, we want this contact to be coming up, which is, so for example, if you consider this as the drain of your PMOS and NMOS, we want the source to be coming out, we want this source to be coming out, and we want the gate to be, we want one of the drains to be coming out for the output. Let's say this is just an example. We can have various combinations of that. So let's say we want this 3 section of the contacts to be coming out of your chip. So what we do is we create a mask 11. Okay, now we remove the mask from the structure, and we have the photoresist present over here. Now we'll etch off the extra titanium nitride we have. Okay, and that is done through RCA cleaning. So RCA is nothing but a solution. It consists of various combinations of various parts of chemicals. So for example, in this case, the RCA cleaning will consist of deionized water, 5 parts of deionized water. So deionized water is a more cleaner form of water. So we have ammonium hydroxide. We'll use 1 part of ammonium hydroxide, and we will use 1 part of hydrogen peroxide. So by this combination, we can create a solution, and that solution is used for etching of titanium nitride, and that process is referred to as RCA cleaning. Okay, we'll cover all of them in the device physics course. So let's wait for it, and let's not get into the chemical formulas for each and every one of them. So we'll cover them in the device physics course. So the titanium nitride is being etched off using RCA cleaning, using the solution that we just explained, and this is how it will look like. Okay, so now you have this contact, so you have this one and you have this one available to be taken to the top level, or to be taken out of the chip. So that's how we'll be going to that's how we'll be doing it through the higher metal levels. So the first level of contact has been done. Okay, and this is the TIN local interconnects that we can use to connect each other locally, and also we can bring this up to the top. So let's try to look into the higher metal level formation from the next video. Thank you. Hello everyone, let's look into the higher level metal formation. So the good news is, if you have looked into the steps till now and if you have understood it well, these steps will remain very similar, very familiar to the previous steps. So there is nothing new that we are going to introduce over here. Only the reasoning why we are depositing certain layers and everything, that will be the theoretical part, is the newer one. But other than that, the steps remains the same. Okay, so let's move forward. So the first step to notice over here is the non-planar surface topography. So the surface topography that you see over here, that's completely non-planar, and it's not very good idea to use the metal interconnects or deposit the metal interconnects on this layer. Okay, there are some problems with respect to metal discontinuities and so on. So we'll talk more about that when we go there. But the bottom line is, you can't use this surface topography for your metal interconnects. What do we do about it? So the best step is to planarize this particular surface. So how do we do it? The next step is to deposit a thick layer of SiO2. Okay, and there is something special about this particular SiO2 that is being deposited over here. It's being doped by phosphorus or boron. Now there are multiple reasons to do this. So one of the reasons to dope it with phosphorus is the phosphorus acts as a protection layer for the sodium ions. So there are some mobile sodium ions that flows inside this SiO2. So we need to take care of that. So phosphorus acts as a barrier or protection against them. And we'll talk more about that when we enter into VLSI technology classes. So let's not talk about that over here. The next step, there is another reason why we use boron. So boron is basically used to reduce the temperature. Now this wafer will be again exposed to certain higher temperature or certain processes which will need high temperature. So boron actually helps us to reduce the temperature of this particular surface. So there are other physics related reasons for this. We'll talk about that when we go to that course. Okay, so if you still look into this surface topography, you still see these hills and valleys present over here. So the next step is to polish this and get a flat surface. and the step is referred to as chemical mechanical polishing, a CMP technique. This is primarily used to planarize the wafer. So basically it's nothing but a simple technique where you take the structure or take the substrate, you topple it upside down and expose it to some machine which actually planarizes the surface. Okay, that's a pretty simple step to say, but it's a mechanically very complex structure. So it's a mechanically very complex thing to do. So that is a step that is used to planarize the surface, and now we are good to go to for the higher level metal interconnects. So what do we do now? The next step is to create the contact holes. So for example, if we decide that we want to create some contact holes over here, let's say somewhere over here and somewhere over here, we do so by drilling some contact holes. So drilling the contact holes is something like you take a pin and create a contact hole over here. Okay, in a broader language, but for a CMOS fabrication process, there is a various step to do it, and we use the same photolithography step to do the contact holes. Okay, so this is how do we do it. So the steps remains the same. Now we are at mass 12. We'll spin this particular structure with photoresist and expose off certain areas with the UV light. We will use mass 12 to protect the remaining layer. So this is the mass 12. We are about to reach mass 16. So the next step is to remove the mask and etch off the SiO2, which is for which we want to drill the contact holes. Now we decide to drill contact holes over here, and as well over here. Okay, so this is how you do it. So when I say we drill the contact layers over, we drill the contact holes over here. So we are actually making this area accessible to the top layers. Okay, that's what we exactly do. So the next step is to remove the photoresist and now deposit a thin layer of titanium nitride. So titanium nitride, so the question is, why titanium nitride? TIN acts as a very good adhesion layer for the SiO2. Okay, that's one of the reason. And second, it acts as a very good barrier layer between the bottom levels or the bottom interconnects and the top interconnects. The next step is to deposit a blanket tungsten layer over here, and this will help us to create a very good contact from the bottom to the top. The next step immediately after this one is CMP, which is chemical mechanical polishing. We'll remove off the extra tungsten that we have over here and planarize the surface. Okay, so this is how your surface will look like now. And the further steps are again pretty simple. You need to use some mask and photolithography techniques to bring this contact holes outside your chip. So let's see how do we do it. Okay, so the next step is to again first of all now we have an aluminum, now we have a blanket tungsten layer over here, which is the contact holes. Now this contact holes has to be connected to a higher metal level, higher metal layer. So we use aluminum as a metal layer. We deposit an aluminum layer over here, and then we pattern this aluminum layer to take it to the top level. So we use again mask 13. Mask 13, the process again still remains the same. Mask 13 is used to block certain areas of the aluminum where you want to take out the contact holes right to the top, and the remaining areas of your aluminum is being etched out. Okay, so this is how we do it. So now you have this aluminum is in contact with the bottom layer over here. You have this aluminum which is in contact with this particular layer. You have this aluminum which is in contact with this layer. So the contacts is being produced, or the interconnect sizes is being increasing as we go to the higher metal level layers. So the next step is to remove the resist, and now you have your second level of metal. Okay, so you have your local interconnect, you have the first level or the zero level of metal, which is local interconnect. You have your first level of metal, which is the aluminum interconnects. Now the next step is to again take this particular metal levels to the higher level metal. Okay, let's see how do we do it. The steps remains pretty simple. You deposit oxide, you deposit SiO2, the same thing that we did for this layer. You deposit SiO2 and you again do a chemical mechanical polishing over here. And the next step is again to pattern the same thing. I have not shown the patterning or the photolithography techniques over here, but we know that there is a mask 14. We will use another mask, which is mask 14, to drill the contact holes. The steps remains pretty much the same. You use the mask 14 to drill the contact holes in a similar way that you did for here, and for here. So now when you use this, you again do the same thing. You deposit a thin TIN layer, and the reason for depositing TIN remains the same. It acts as an adhesion layer for the SiO2 and also acts as a barrier between the lower metal layers and the higher metal layers. And the next step is to again deposit tungsten. That the same thing that we did over here and over here. It's basically now we are making the contact holes. So the steps again from the bottom till the top remains the same. You have your first level of interconnects, you drill contact holes. You have your second level of interconnects, you again drill your contact holes. You have your third metal of you have a third layer of interconnects that we are going to deposit now. It will look something like this. Okay, and you will use mask 15 now, because this was mask 14. Now this is the mask 15 to drill to make the third level of interconnects over here, and which is the, if you see the thickness of this one and this one is a bit thicker than the bottom layers, and that's what it exactly happens. So if you look into the outside pins of your chip, it looks much thicker in size, and this is the reason for that. As and when you go from bottom to top, the thickness of your metal layer or thickness of our interconnects is actually increased. And once we have done that, the higher steps again remains the same. You deposit and again a layer of Si3N4 or SiO2. So it could be anything. Basically, Si3N4 is the one which is used to protect the chip. So assuming this is the last level of your chip, this is where your interconnects come out. We'll use the Si3N4, which is a stronger dielectric to protect the bottom layer from the top. So this will actually protect your chip. This actually acts as your protection layer for your entire chip. Okay, and finally we'll use mask 16 to drill the contact holes and bring up this particular contact outside your chip. And now this is how your CMOS 16 mask process will look like. So you have your contacts, you have your source, you have your gate over here, you have your drain over here. Drain is connected right from this point and reaches this till this point. You have your source over here, you have your gate over here, you again have your drain over here. So this was your 16 mask process, and this finishes the fabrication steps that we wanted to do now. The next lecture onwards are basically entering into the software techniques of your layout tool. So let's try to talk more about the tool point of view from a layout tool point of view and from the software point of view from the next video. Thank you.
And when you type box, so that will give the dimensions of the box. You can see, you can try this. And following that, we build the CMOS step by step. So first we do, since I told you the first layer is the locali, so we lay our ground and the VDD pins on locali, and then since we will be taking connections on metal 1. So the standard cell rows are in metal 1, the power and the ground lines are in metal 1. I will show you where do we have the definition, that why do we have to have the standard cell rows, power and ground in metal 1. Where do we have that definition? So this is and the dashed lines, as I had told you before, that's the end well. So you can see this is the end well. This was the first thing we drew, the fixed B box. The purple thing you see hidden behind the dashed line is the metal 1. The bluish line, light blue line, is locali. And there is one more layer, N substrate diff, that is actually behind this locali. That is one of the design rules you need to fulfill if you want to have a contact. So now see, we just have made the layers, we have not made connectivity. So this square bluish checked contact is the contact between the the first layer, that is the local interconnect layer, and the metal 1. So that is the contact, that is called Li con. So we'll just go to the layout window and see where that contact is. So yeah, this was what I was talking about, Li con. Li con is the connectivity between the locali layer and the metal 1. Before we make that contact, we have to make a contact between the, now for example, the PMOS. The PMOS is actually inside a well. The dashed line inside the well. There needs to be a contact between the N well and the Li con. That is this. As you can see, that is more clear in the web page. You can see here this crossed line, that is the N substrate contact. That is the first contact. That is the contact between the N well and the locali. So that first layer connectivity is done, and then you need to have contact between locali and metal one. So this is this checkered line. This checkered box is L-icon. I have marked it here. Similarly, for NMOS, since NMOS there is no well, so it's direct P substrate. So you need to have first contact between the P substrate and the local I layer. So that is this, you can see here. It's P substrate contact. And then you need to have a contact between the local I layer and the metal one. So that is this L icon, right? Hope that's clear. You just it's logical, right? So for PMOS there is N-well. Above that N-well there is local I layer. Above local I there is metal one. So you to connect these layers, first you need to connect the N-well and the local I. For that you need N substrate contact. Yeah, N substrate contact. N substrate contact will ensure connectivity between N-well and the local I. Now you need to have a connectivity between local I and metal one. For that L icon is used. Similarly for the N side, for the ground rays. So now that you have fixed your ground and the power and the ground rays, all you need to worry about is the logic. So you need to follow the DRCs. So Magic is one of the interactive DRC tools, as in when you have a DRC, it will show up in the DRC. Right now the DRC is 0. So for example, I remove this layer. Okay, this is fine. This won't cause any problem. I will do one thing. I'll just try to remove this. Right now, as you can see, the DRC has changed from 0 to 7, and this dashed lines, this dotted line, white dotted lines is the error. To know the error, you go to this DRC tab, and then you click DRC, find next error, and the tool will zoom into where the error is. And if you want to know what actually is the error, once the tool highlights this error, it will be written in the TKCon window. So these are the errors. These are the DRCs which you're seeing. This constraint, the physical DRC, is what getting violated. So this is important from the manufacturability point of view, because if the DRCs are violated, it cannot be manufactured. So you have to ensure your final design needs to be DRC clean. So in this case, right now, if we can see, if we can troubleshoot this. So first, they will ensure that this entire area is N-well. So they will select that area, and this is the layer, all well P lane. So this is basically the N-well. So if you want to select the layer, move the cursor over that layer and press your middle mouse button. Right. So the DRCs have been reduced from 7 to 5. So this is what I was talking about. It's an interactive DRC. As and when you keep doing, this DRC is reduced. So that we have covered this area with N-well. Second, N-well, over N-well we have, so there is no L icon. So this is purely metal one. So we'll select this area, and then we will use metal one. Metal one is here. Right. So our DRCs are back to 0. So I select it, I will centralize it. So this is my inverter. So so this is well and good. This is all layers. So how do we know what is the logical functioning of this inverter? For that, we would first extract the SPICE, and post that we will do simulations on SPICE in ngSpice open source tool. So to extract it on SPICE, so we will open the TKCon window, We will right now see where we are. We are in this directory, right? This is what we had cloned, OpenLane VHG standard cell design. So the first step is to create an ext file, extraction file. So that command is extract all. So this has said that extracting our design into sky underscore inv ext. So let's go to that location. Where was it? Yeah, here. And do an ls minus ltr. Let's see if something new has been created or not. Yes, it has. Sky130inv.ext. So next what we'll do is we will use this ext file to create the spice file to be used with our ngSpice tool. So for that, what you need to do is you do x2 spice, extract to spice, and I think the command is extract to spice. Yeah, that's it, x2 spice. That's the command. So we use a c thresh 0 r thresh 0. So doing this will extract all the parasitic capacitances also. Since these are actual layers, this will have parasitic capacitance. So we'll do this. So this has not created anything new. So you can see it's the ext file is there. Nothing new has been created. Now we will do x2 spice. That means the ext file to spice. Let us see ext2 spice finished. So let's see if anything new has been created or not. Yep, it has. Spice file has been created. Now let's clear this window and let's see what's inside the spice file. Okay, so not much. So before we begin our simulation, let's first understand what the spice deck contains. Yeah, let us first understand what the spice deck stands for. So as you can see, we first have this PMOS, this M1000, that is a PMOS. How do I know it's a PMOS? You can see the model name PShot. Similarly, this is NMOS. For PMOS, this Y is uh, the drain, the gate, followed by the source and the substrate. Similarly, this is drain, gate, source, substrate. So let's understand the netlist first. I'm going to draw on the screen. My drawing might be a little horrible, but I hope I can get the message conveyed. So this is our PMOS. It has got source, drain, substrate, and gate. So for the PMOS, you can see the PMOS M1000. Its drain is connected to Y. So it is connected to this node. It's important to realize here that the alphabets are just nodes. It's not a value, it's not a voltage. It's connected to node Y. The gate is connected to, you can see here the gate is connected to node A. The source and the substrate is connected to node PWR. Right? So this is what the first line says. We are done here. And the second line says there is an NMOS. There is NMOS. Whose right? It says that its drain is connected to Y. So that means this connection is complete. And it says that its gate is connected to A. That means these two are connected. Then it's saying that its source and substrate is connected to a node. Remember, it's a node whose name is VGND. Node's name is VGND. It's not P, it's T. Right? Okay. Now what all we need to do for this transient analysis? First, we would want this V ground to be connected to a ground, let's say VSS. Then we would want a supply voltage that needs to be connected from VPWR to ground. So we will create a node. We create extra node, say give the node a name 0, and we will create a VDD with a value of 3.3 volt. And now we have to sweep it. We give a sweep in voltage, a pulse voltage that needs to be connected between A, the input pin, and the V ground or 0. We will give it a value of the voltage value of VA, just the variable name. So we need to do this, and this connection. We have to define this connection. The connections which have been designed by this spice deck are these double tick ones. Yeah, that's all. Double tick ones. A and Y. We have to define the single tick ones. So we will do something. You can see if I can. I'll just remove everything. Clear the screen. Okay. Close it. Then right. So this is my screen again. I hope you can see. Yeah. First things first, we need to ensure that the scaling is proper. Right now the scaling is any dimension into 10,000 microns. So 37 into 10,000. That is not what we need. We need the values to be in the grid value which was specified in the layout. Since if you recall this spice we had extracted from the layout. So the layout minimum value of layout window is the measure, the grid here. So this is the measure of the any measurements that needs to be taken in the spice file. So we'll zoom in a little bit. We'll see this box, one box, and see the dimension of the box. Dimension of the box is 0.01. That's why we edit. Where was it? Sorry. We edit the scale to 0.01. Any measurements will be with respect to this. So the width will be 37 to 0.01. I think it's 0.37 microns. So this is done. Similarly, now we have to include the PMOS and NMOS lib files. So that for that you do dot include, and if I recall correctly, where was it? If I recall correctly, it's inside the libs folder. CD libs. Yeah, these two files. So to specify that, we have to do /libs, go to libs folder, and for pshort, similarly we will do the same thing for nshort. nshort.lib. So these two files are included. We will comment out this, or else, because we are trying to input the controls also, transient analysis also in this netlist. So we will put it as a command. This is fine. This definition is fine for both the transistors. Now we need to make the definition for the supply voltage first. So we will create a variable VDD which is connected between VPWR and the node 0, which has a value of 3.3 volt. So this created the supply voltage. Similarly, we will create a V ground. V ground is already there. We create VSS. That is the voltage connecting between the VGND and 0. VGND and 0, whose value is 0 volt. Fine. The ground and the supply is done. Now we need to specify the input pulse. we'll get a value of VA, let's say VA, which is connected between the gate and VGND, which is now equivalent to the node 0 having a value of 0. And this is how we give a pulse value. Pulse. The pulse low value is 0 volt. Pulse high value is 3.3 volt. Pulse starting point is 0 nanosecond. The pulse is rising, the rise time is 0.1 nanosecond. 0.1 nanosecond the fall time. This 2 nanosecond is the on pulse width, and 4 nanosecond is the time period. So this is how we define a pulse in the SPICE deck, and post that we will also include the type of analysis which we want to do. So this I have already, this is the analysis. This is how we specify the analysis. We do a dot tran. Dot tran is for the transient analysis, sweep from 1 nanosecond to 20 nanosecond, and then you run it. So this is how you create the flow for SPICE deck. So we need to run this in the ngSpice open source tool. So before that, we'll just see what is inside the model files. So as you can see, this model files actually starts here. So this is the name for the model file, pshot underscore the PMOS model name, pshot underscore model.0. So you can see all the parameters that is defined under this SPICE model file. There is one more small modification we would have to include in our SPICE deck. As you can see here, this M1000 I had told you is a PMOS. How does the ngSpice know it's a PMOS? By using this. But this is not the model name for PMOS. What we saw in the SPICE model file was this pshot underscore model.0. Only when you specify this will it will it take all the SPICE parameters from the model file and assign it to this model and do the simulation. Similarly for NMOS, it's .0. Now I think our SPICE deck is ready. To run our SPICE simulation, what you do is ngSpice, that is invoking the tool, and pass this as the source file. So you can see these are the values it has taken. Now to see the plot, you have to do plot. What do you want to see? You want to see the output versus time, sweeping the input. Our output is Y, time is the time period, and the A is the input. Now this is what we get. Okay, we can see some spikes around here. We will do one thing. I think the C load is very less. Let's open the SPICE file again. The C load is what you define between the output pin, that is Y pin, and the ground. So which is here C3, that is 0.24. Let's give it some higher value, say a 2 femtofarad. That seems reasonable. Now let's run this SPICE simulation again. Now let's plot output versus time, sweeping the input. Yeah, little better. So now that we have our transient response, our next objective is to characterize a cell. So characterizing a cell means to find the value of 4 parameters. We would need to find the value of rise transition, that is the time taken for an output waveform to transit from a value of 20% of the maximum value to 80% of the maximum value, VDD. Similarly, the fall transition is the time taken for the output to fall from 80% to the 20%. Similarly, we have two more values, that is the fall cell delay and the rise cell delay. That is also called the propagation delay. So that is the time difference between the 50% of the difference between 50% of the output and 50% of the output. Now when it's a cell fall delay, it's the difference between the time period when the output has fallen to its 50% and when the input has risen to its 50%, that time difference. So it might sound a little confusing, but I will show you one of each. So to begin with, we will first check what is the rise transition. Rise transition is the time taken for the output to rise from 0 to, to rise from 20 to 80% of the maximum value. So the maximum value right now is 3.3. We have defined in our spice deck. So a 20% of 3.3 should come around 0.66. So 0.66 is somewhere around here. To select a particular region, all you have to do is just use your right mouse button. The right mouse button itself creates a box, unlike Magic, where you have to first click the left mouse button, then the right mouse button to make a box. Here, just the right mouse button creates a box. It will open up a new window. As you can see, 20% value is 0.66. So this is little congested. We'll zoom it even more. So this should give a better value. Yeah. Where is 660? Yeah. So let's click here. So when you click on this point in the ngSpice window, you can see the values getting printed. So 0.66, the y value. For that, the x value, that is the time, is 2.18. Let's go back. We close this one too, not the main one. And the 80% should come as 2.64. That should come somewhere around here. 2.64. Zoom it up a little bit. 2.64 the value is here. Now let's check 2.64. Yeah, value is 2.64. Difference between these two values, this x0 value and this x0 value, should give you the rise time. So that should come around 2. I'm just using my calci. 2.4. Sorry, 2.245. That is minus 2.181. That is 0.064, if I'm not wrong. 2.245 minus 2.18, that is 0.064 nanosecond. Similarly, you can find the fall transition. That means when the output falls from 80% of the value to its 20%. The difference of those two values will be the fall transition, and it would be as one of the assignments. Now let's check for the cell fall delay, which is the propagation delay when the output is falling between the 50% of the values. I will just do rise for both. So when the output is rising, the 50% of the rise, that is 50% of 3.3 is 1.65. So we will find the time difference between input and output when the value is 1.65. So I think 1.64 and 1.66. will zoom it a little more. 1.65, yes. The 50% of the output is crossing at this time. Clicked it. For the input, it is this point. Now when we go to our spice window, you can see, yeah, these two values. Now the difference between these two values will give you the cell rise delay, that is propagation delay when the output of the cell is rising. So let's just calculate 2.21211. minus 2.150. Yeah, that is 0.061. So that is our cell rise delay. So the same way you will find for cell fall delay, which will be following in the assignment. So yes, you have successfully characterized a cell for a given temperature. Right now the temperature you can see here is 27 degrees Celsius, the room temperature, normal temperature. This is how the characterization actually works. You have actually got a taste of how the library characterization work in the VLSI industry is done. It's done for different process, for different PVT colors, the process, voltage and temperature, and that's how the timing library is built. So our next objective would be to create a, this is our layout, right? Just zoom in. Shift Z to zoom out incrementally. So S, and so this is the layout which we have. So we have characterized our inverter. Our next objective is to use this layout and create a left file, and that left file we will be using in our open lane, and plugging this cell, we will make a custom cell, we will give it a custom name, and we'll plug this cell into our Pico RV32 core, and we will see if open lane takes our cell or not, what are the challenges we face. So that will be the next which will be following up. Hope this was a learning session. This is where you actually do something. So this is a good session. This is a good workshop. I would request you to have a little hands-on on this. So till then, let's meet again. Happy learning.
Hello everyone, and welcome to the lab exercise for this VSD presentation on open source EDA tools. While the first part of the presentation covered many topics on the history of open source EDA tools, writing software, discussion of different tools, and so forth, there's obviously not enough time in a lab exercise to cover more than just a little bit of that. So this lab exercise will just concentrate on one topic, which will be Magic's DRC engine. I'll start with a more in-depth overview of how Magic does DRC than I gave in the lecture part of the presentation. This will include a number of topics, like why Magic has different DRC styles for a single PDK, what are the basic rule types, what are some of the more complicated rule types, and a discussion of some of the rules that are handled separately from the interactive DRC engine. The lab itself will involve working through a set of document style layouts, each of which demonstrates a particular set of rules for one process mask layer, either violating a layer and showing an error, or not violating a rule and showing the layout to be DRC clean. These layouts are all done using the Google Skywater PDK. Because the Magic technology file for the Google Skywater PDK is still a work in progress, a number of these rules are either unimplemented or implemented incorrectly. The goal of the lab will be to find problems in the DRC section of the Magic tech file for the Skywater process and fix them. Because fixing a simple error is not a particularly difficult problem, I'll be challenging you to warm up with a simple problem. And after that, the main challenge will be to find a not so simple problem and find a way to implement that in the Magic tech file rules. Before I begin the lab, I want to show you a little bit about how Magic performs DRC and Magic's syntax for DRC rules. Generally speaking, where you want to go when you want to know something about Magic is the website on opencircuitdesign.com. You can go there now as part of the tutorial, so head to the web page at opencircuitdesign.com/magic. On the left-hand side, you'll see a column of buttons. There are two of these that you will find particularly useful, the one that says Using Magic and the one that says Technology Files. Since this lab exercise is completely related to the tool Magic, you will need to know at least some of the basics for getting around Magic. I can't spend the tutorial time showing you how to do all of the really basic stuff like drawing, erasing, zooming, panning, and so forth. There are some simple tutorials on the website that give a good introduction on the basics for using Magic. If you're not already familiar with Magic, you'll want to work through the first 2 or 3 of these tutorials to learn the basics. So, on the Magic web page, click on the Using Magic button, and then click on Magic Tutorials to take you to the section listing the online tutorials. I mainly recommend looking at Tutorials 2, which is Basic Painting and Selection, and Tutorial 6, which is the Design Rule Checker. Most of the rest won't be particularly relevant to this lab exercise. Going back to the top of the page, the other useful place to go here is the Magic Command Summary. Magic is a GUI-based layout drawing tool, but it is really at its core a command line driven tool, and while there are keyboard shortcuts and menu items, a lot of things you need to do in Magic are best done from the command line in the console window that shows up along with the layout window. If you need to learn about any command syntax, and I will be typing in a lot of commands as part of this tutorial, then the online command summary is the best place to go. Now, for a discussion about the technology file. The technology file is one single setup file that tells Magic everything it needs to know about a process. This includes a lot more than is usually found in a single file for other tools. Not only does the technology file declare all the layer types and colors and patterns, but it also defines electrical connectivity, DRC rules, GDS generation rules, device extraction rules for generating netlists, rules for reading LEF and DEF files, rules for interactive wiring, and much more. To find out all about the syntax used in Magic's technology files, click on the button on the web page that says Technology Files. Then click on the link, the Technology File Manual. Again, there's not time in the lab to discuss every part of the technology file syntax, but the information is there if you want to look at it. For the purpose of this lab exercise discussion, there are two sections we will want to look at, the DRC section and the CIF output section. A quick note about CIF, C-I-F. You'll see the word CIF used a lot, and if you're not familiar with it, it was once a common output format for mask data. It stands for Caltech Intermediate Format and is a human-readable ASCII format. As part of the ASCII nature of it, all mask layers have names rather than numbers, as they do in the non-human readable binary GDS format, which you're probably more familiar with. We'll not be using output formats in the lab, but just be aware that CIF is sometimes used interchangeably with GDS in the Magic text file and the Magic documentation, and just indicates mask data for a layout. In the table of contents, click on DRC section. There's a lot of information in here, but mainly you want to know the types of rules available and the syntax for them. Since for the lab you'll be editing an existing text file, you can work mostly by example, but it's likely that you'll want to go to the documentation from time to time to check the syntax or see what options may be available for a rule. The basic DRC rules are what are called edge-based rules. They work by finding the edge or boundary between two layers and then checking the area in front of or behind the edge for anything that is violating a particular type of design rule. The rules are pretty straightforward, so you'll find things that you would probably expect, like width and spacing rules and surround, extend, overhang, and so forth. Sometimes, if nothing in those categories seems to fit, there is a general purpose edge rule that can be used to describe almost any edge-based situation. Reading through the section on the edge rule will give you a good idea of how all the other rules work. There are also rules that are not edge-based. The area or minimum area rule is one of these, as is max width, rect only, and angles. But in some cases, rules are neither edge-based or fit any of the other rule types available in the DRC section of the text file. For those situations, Magic has a different type of rule checking, which is to run a sequence of geometrical manipulations using various operators, such as Boolean operations, to produce a result that can then be passed back to the regular DRC engine and treated as an edge rule. This topic will be covered in detail later in the lab, but for now, go back to the top of the web page and click on CIF Output section. Partway down into this section, you can find all of the operators and how they work. The Boolean operators are the easiest to understand. OR and not, and grow and shrink are pretty easy to figure out. The bloat commands are a little bit more complicated, and there are a handful of specialty operators to cover a bunch of different situations. Again, like the basic DRC rules, you will most likely want to work by example from the text file used for the lab exercise, but you'll want to know where to go in the online documentation to find out what's available, how and when to use it, and what the syntax is. Of course, none of this matters if you don't have a technology to work with. Fortunately, we now have the opportunity to use a fabrication process technology that has been open sourced and which has all the details posted online courtesy of Google and SkyWater. This is the Google SkyWater Sky 130 130 nanometer process, and details of it can be found in various places. The two main sources of information are the PDK itself, which can be found on the GitHub under https://github.com/google/SkyWater, and the documentation, which can be found at https://skywater-pdk-136.org.readthedocs.build. The GitHub site is good to know, but we won't be using it for the tutorial. The documentation site is critical to the lab, and you'll want to have a browser open to that while doing the lab. The sidebar of that web page has a section, Design Rules, that you will want to click on, and from there you can click on the names of specific rule sets and see all of the rules associated with the process with illustrations. These rules will correspond directly to layouts used for the lab. In this slide, I have a pointer to where you can find the layouts done in Magic for the lab exercise, which should also have been provided to you as part of the lab. There are about 24 of these layouts, and they correspond to the DRC documentation, which I just mentioned. As is usual for design rule documentation, the rules are grouped together into sets and are generally sorted by mask or design layer. So in the documentation, you'll see references to obvious drawn layers like Metal 1, Metal 2, Via, etc., to drawn front-end layers like InWell, Diffusion, Poly, etc., and to implant layers like N+, and P+, thick oxide, and transistor threshold tuning implants. There are occasional sections for specialty rule sets that cover some specific device, like, for example, a MIM cap and extended drain MOSFET, and so forth. As is typical for Magic and the way it does tech files, and which was mentioned in the lecture part of the presentation, the implant-like layers are automatically generated on output, so you won't see them in the layout view. The only way to view those layers is to use Magic's SIFC command to highlight the areas where that layer will be generated in the output. In these example layouts, where a layer can't be seen directly, there will be a labeled message at the top telling you what layer name to use with the SIFC command so that you can see that layer. First, make sure you're set up to view the layouts. This lab exercise is largely self-contained, so you don't need the complete infrastructure of files and tools around the Google SkyWater PDK. Since Magic has its own unique format, there isn't much that Magic needs from the SkyWater files. In fact, the Google SkyWater repository files are built with the help of Magic for extracting, generating views, and more. So it's necessary that the Magic tech file should be created first, as a lot of stuff depends on it. So its contents are largely independent of the repository contents. To work with the full Google SkyWater PDK, you would want to get the PDK from GitHub and install it, and download my OpenPDKs installer from GitHub, and use OpenPDKs to install a version of the Google SkyWater PDK that does important things like creating the Magic tech file. But since the PDK is still under development while I'm preparing this laboratory exercise, I've instead just packaged up the current unfinished tech file for Magic along with the lab exercise layouts and bundled them into a tarball. I'm assuming that you're working on a Linux system and that you have followed the instructions, and so you put the tarball in your home directory and untard it there, so you have a lab exercise installed into your home directory under a subdirectory called cad/design/drc tests. In that directory, you should have the set of 24 or so files with the .mag extension, which are the layouts in Magic's file format. Also in that directory, there is a file called .magicrc, which is the startup script for Magic. One thing it does is to tell Magic where to find the technology file. Because this lab exercise is self-contained, there is a copy of that technology file in the same directory. That's not recommended practice generally, and if you use the open source, if you use the OpenPDK's installer, it would be elsewhere in the system. But since the purpose of the lab is to make changes to the technology file, you'll want that copy locally, where you can find and edit it. To start the lab exercise, you should cd to that directory, cad/design/drc tests. You can edit or view the .magicrc file to see what it does, but mostly all it's doing is to load the local version of the tex file. Because the startup script takes care of loading the tex file, you don't need to specify it on the command line, so you can start Magic with just magic on the Linux command line. My own preference is to use magic-d OGL or magic-d XR because the graphics are, in my opinion, a lot better than the traditional or default X11 graphics. Let's look at an example of a fairly simple set of rules, starting with Metal3. The name of the file is met3.mag, so run magic-d XR met3, for example. You can also just run magic from the command line and use the menu option File followed by Open to load the file. This is what you should see in the layout view. In this view, you can see that there are a number of independent example layout geometries, and most of them show some kind of DRC error, which is displayed by the interactive DRC engine as a white patch where the error has been flagged. Each of these little examples is labeled with a name, and that name calls out a rule number in the Google Skywater documentation. Those rules can be found on the Google website at the readthedocs.build URL, which I told you earlier to have handy in a web browser. From that website page, there's a menu on the left-hand side where you can click on the down arrow and expand the section Design Rules, and then click on Periphery Rules. From the table of contents on the right side, you can find M3 in the list, and click on that to automatically scroll down to the section on Metal 3. There you'll see each of the rules listed corresponding to one of the small examples in the layout. Note that there is a column listed for flags in the documentation, and where that column says CU, it refers to a copper backend process variant that doesn't currently exist in the Skywater Sky 130 process, so those rules do not need to be implemented. Let me make a quick note about using magic. Most common commands have single key hotkey type equivalents, and a number of common commands can also be reached by a menu item. But the usual way to interact with magic is through commands on the command line in the console window. The interface is designed so that you can reach the console window directly from the layout without constantly moving the pointer between the two windows. If you are in the layout window, just type the key colon or semicolon. Once you do that, all keystrokes are redirected into the console window until you hit return or enter. So you can type in and execute commands while you're still working with the pointer and the cursor box inside of the layout window. I'll be doing those kinds of commands throughout the lab example, so you'll need to be aware that that's how I'm doing them, by typing colon and then entering the command on the keyboard. If you're following along, you can do that now. Use the mouse left and right buttons to position the cursor box, as it's called, around one of the example areas. Then type colon and type drcy and return. The command should show in the console window as you type it, and when you hit return, you should see the response, which is the rule which is being violated where the error shows in the layout. For Metal 3, all rules are related to drawn layers that you can see, except for rule M3.4, which from the documentation you can see is via2 must be enclosed by Metal 3 by at least, and the value is 0.065 microns. As part of Magic's habit of using many derived layers, a via is actually a kind of derived layer in which the drawn via represents an area that is filled with contact cuts. To see that visually in the Magic layout window, draw a large area of M3 contact, which you can do with the paint command or by hovering the mouse pointer over the M3 contact icon on the sidebar and either clicking the middle mouse button or typing the P key. Then, with the cursor box still around the area you just drew, type the command sifc via2 with via2 in caps. You'll see a bunch of black squares appear inside the area. These are the contact cuts, and they don't actually exist in the drawn layout view. What they represent is the mask layer for VIA 2 that will end up in the output GDS when you generate GDS from the layout. They are created from rules in the CIF output section of the TeX file, which has a special command for telling Magic how to draw contact cuts inside a drawn contact area. The view you see in the layout window is called a feedback entry, and it sticks around for as long as you want, and you can dismiss it with the command feedback clear, or feed clear for short. While it's still showing, you can prove that the rule VIA 2 must be enclosed by metal 3 by at least 0.065 microns is being honored by Magic's way of automatically creating contact cut squares. This technology file is set up to work on a typical grid of 0.01 microns. This helps make a layout a bit simpler by not having to work on a 5 nanometer grid, but if you want to move the cursor box around on a 5 nanometer grid, you need to run the command snap internal or snap int. Otherwise, you may not be able to align the cursor box with the edge of the via shown in the CIF-C view. With the cursor box positioned between the contact cut and the drawn via edge, you can measure the distance using the command box or key B. For what I'm showing here, the relevant distance is the width of the box, and that shows up in the console window as measuring 0.065 microns or larger. Because the contacts are automatically spaced and centered in the area, the distance to the edge may be larger than the rule minimum distance, but never smaller, no matter how you draw the area. That's why the rule is listed as correct by design. I chose to start with layer metal 3 as an example because all of the rules are simple and there aren't very many of them. But let's look at something else, a layer which has a rule that is incorrect, but that is simple to fix. This will be the first exercise of the lab. I'll find one of them to show you how it's done, but then you'll have to find one by yourself. There are plenty of rule implementation errors to go around in this unfinished version of the TeX file, and they should be clearly indicated with the label. In Magic, load the file poly.mag. Here you can see a lot of rules implemented, and a couple of them have helpfully been flagged as incorrect. Let's look at rule poly.9. Check the website for the rule description. It says, poly resistor spacing to poly or spacing, no overlap, to diff tap, and the rule distance is 0.48 microns. If you want to know what types are in the layout drawing that you see but don't recognize, you can select a drawn figure with the S key and then type the command what. Here you see it says that this is type in polyres, and you can see that the type on the bottom is poly. So this figure correctly depicts the rule poly.9 because it shows the distance between a poly resistor and regular poly. You can put the cursor box between the poly on the bottom and the in poly res above it and see that the box measures just 0.22 microns, which should be showing a rule violation. Clearly, it's not. So, what to do about it? Okay, first we find the error. So use your favorite editor, Vim or gedit or Nano or whatever, to look at the file sky130a.tex. The DRC section starts on line 4702. First, I want to look to see if I have at least attempted to create rule poly.9, so I search for poly.9 in the file. I find it in two places. Looks like it is defined for the distance between np-res and nsd, and later for the distance between xhr poly and diffusion. Apparently, no attempt has been made to implement the distance rule for the poly resistor to poly. This can be added easily, which is why I use this as an example of an easy rule to fix. Just add another spacing rule to cover what's missing. I need to add several here. First, from XHR poly and UHR poly to regular poly, I'll make a copy of the rule and change all diff to star poly, where the star in front is a shorthand meaning poly and all contact types containing poly. I'll go look through the aliases section of the TeX file to see if there's anything more appropriate though. And yes, there's all poly non-res, which seems to best fit the rule, so I'll use that instead. There, I've implemented that rule. Then back to the other one and do the same thing. Now save that. Now I don't need to restart Magic to check this change. I can run this command on the command line. Tech load sky130a.tech. I get a pop-up warning about how it's dangerous to go mess with the tech file while you're still editing something, but we're only changing DRC rules, so it's okay. Now, since the tech file got loaded behind the curtains, so to speak, the DRC engine needs to be told that it has to check everything again. So run the command drc check. Now I see that all of these spacing rules have been fixed. The rule is now correctly implemented, and the spacing between the poly resistors and poly is now flagging an error. But is the rule really completely fixed? Note that the rule said that it was for distance from a poly resistor to poly diff or tap. I just implemented the rule for poly, but what about diffusion and tap? Actually, there's not even a diagram for this. It was accidentally left out. Let's fix that. We'll need to copy the 3 resistors. Because there are a number of different varieties of diffusion and tap, we'll make several copies and check against N diffusion, P diffusion, N tap, and P tap. In Magic, those layers are called NDiff, PDiff, N substrate N diffusion, or NSD for short, and P substrate P diffusion, or PSD for short. N-type diffusions are always drawn in green, and P-type diffusions are always drawn in a tan color. Let's draw those diffusion layers close to the poly resistors. Since we're not checking diffusion rules here, it's helpful to draw an N-well under the P diffusion and the N-tap. That cleans up irrelevant errors, so you can see just the errors related to the distance between poly resistors and diffusion or tap. Clearly, the XHR and UHR poly resistors are properly showing the distance violation, but the N-polyres resistor is only flagging the distance to N-tap. You can see where that happens in the rule file. There is only one rule implemented for N-polyres to N-tap. This is easily fixed using the same all-diff used for the XHR poly rule. So fix that, then do the tech load command again, then do drc check, and now all the rules are correctly identified. Now it's up to you to find a similar simple rule to fix. There are plenty of incorrect rules identified in the layouts. Look for simple rules, which are basic width, spacing, or area rules, and maybe some that can be implemented with the overhang or extend rules. You can look at the online version of the technology file documentation on the Open Circuit Design website for Magic to check what all the rule types are and what the syntax is. Are you ready for a challenging example? A challenging DRC problem is one that can't be described by any of the simple DRC rule types in the DRC section of the Magic Tech file. Instead, you'll have to figure out how to describe the area as a geometrical construct, very similar to the way that Calibre describes error checks in a Calibre rule deck. You'll want to use the CIF output section Boolean operators like OR, AND, grow, shrink, and so forth to work in a way that after all the operators are applied in sequence, whatever is left over is by definition an error. There's a way to tie this into the DRC section of the tech file. That uses a rule type called CIF max width. This is part of a set of rules that checks layers exactly as they appear in the GDS output, even though those layers aren't something you can draw directly in the layout. There are several of these so-called CIF DRC rules with basic width and spacing varieties. But the CIF max width rule, specifically used with a width value of 0, is the most convenient to use, just because the strategy of defining an area as being stuff left over after doing a bunch of operations is fairly easy to understand, and also is familiar to those who have worked with commercial DRC tools. Let's look at an example in the tech file. The first one of these is in the DNwell, or Deep Nwell section of the tech file, which, by the way, doesn't correspond to the way that rule sets are organized by Skywater, which has these rules under Nwell. When used the way it's written here, the rule always is specified with width being 0 and with the bend_illegal option. All that really matters in the command is the use of a layer name, in this case called nwell_missing, which is a layer defined in a special CIF output section in the tech file. All of the heavy lifting, so to speak, is done in SIF output. The rule itself you can find in the documents, rules NWEL.5 and NWEL.6. The text file says NWEL.5a and NWEL.7, which itself is an error that needs correcting. The NWEL.5 rule says that NWEL has to extend beyond deep NWEL by at least 0.4 microns. The NWEL.6 rule says that NWEL has to extend inside deep NWEL by at least 1.03 microns. You can see an example of the rules being violated if you load the layout NWEL.mag from the set of examples and look at the layout labeled NWEL.6. The deep NWEL is shown in yellow stripes and the NWEL is shown with a green dot pattern. The point of the rule is that the edge of the deep NWEL needs to be covered with overlap all the way around by a ring of regular NWEL. The outside distance rule could be implemented with a simple surround DRC rule, but the inside distance can't be captured with a simple edge type rule. Let's go find where this layer is described in the SIF output section. First, we need to go find the style called DRC. This corresponds to the line SIF style DRC that's at the top of the DRC section, and which tells the DRC engine that the output style called DRC is the one used for the DRC rules. So the way the SIF max width DRC rule was implemented with width equal to 0 implies that the NWEL_missing layer is what's left over if either the inside or outside dimensions of NWEL overlapping deep NWEL doesn't reach the required distance. As an aside, note that everything in the SIF output DRC style is implemented as a temp layer rather than a layer. In a regular SIF output section used for generating GDS output, only things defined as layers will get output. All the temp layers are basically supporting layers needed to get the right result for an output layer, but not appearing in the output themselves. Temp layers have the unique feature that they can be used as building blocks for other layers or temp layers. Since the DRC style doesn't produce any GDS output, then there's no point in creating normal layers in it. So everything is a temp layer. So back to the rule. The NWEL_missing temp layer is relatively straightforward. First, it depends on another temp layer called DNWEL_shrink. The DNWEL_shrink definition is above it, and it takes the DNWEL layer and shrinks it by 1030, which is in nanometers, and is the required distance that the NWEL must overlap DWEL on the inside. So what DNWEL_shrink represents is the largest open area that you can have inside the area of the drawn deep NWEL. Now the NWEL_missing temp layer definition starts with the DNWEL layer. Then it grows it by 400, which is the distance required by the surround rule in nanometers. That gives you the smallest NWEL area that is needed to cover the deep NWEL layer. Next, the rule does an AND NOT operation with the DNWEL_shrink layer generated before it. Remember that the DNWEL_shrink was the largest open area, that is, an area without any NWEL, that you can have inside the deep NWEL layer. So NWEL_missing and not DNWEL_shrink is a ring-shaped area that contains the least possible amount of NWEL that satisfies both the outside surround and the inside overlap rules. That means that if any of the area does not contain NWEL, then one of the two rules is being violated. So the last operation in the rule is to do AND NOT NWEL, and that will result in something left over if any rule is violated. Now that leftover bit gets passed back to the SIF max width rule, and if there's anything left over, that gets flagged as an error. In the layout, you can see that by putting the cursor box around the NWEL.6 drawing, first you need to do the command SIF OStyleDRC because you can only see layers for the SIF output style that is selected for output. Then do SIF C DNWEL_shrink to see that area. Then clear it with feed clear and do SIF C NWEL_missing, which shows the area that gets flagged with the error. You can manually remove some of the NWEL and see what effect that has on those areas. Since you will want to use CIFC for looking at actual output as well as checking on geometry created by the DRC CIF output style, make sure you know what style is active and make the correct style active with CIF-O style when you need it, because only one style can be viewed at a time. Note that any edge-based rule could in principle be made with these CIF output operators. But also be aware that generating these layers is very compute intensive and will slow Magic way down. To keep Magic from getting bogged down by these compute intensive rules, it's best to try to use the simple DRC edge-based rules whenever possible, and to put the CIF output rules into a separate style variant that can be run on demand, but can be prevented from running most of the time during interactive layout so it doesn't slow things down. Those rules are best left to a batch-style DRC processing, but they can be checked by the user from time to time as needed. In this tex file, the two variants are named DRC Fast and DRC Full. DRC Fast is intended for working on back-end metal layers and large synthesized digital designs without forcing Magic to check all the layers below metal. DRC Full will check everything, which can keep up with the interactive use as long as it's in a relatively small layout. You can switch between them using the commands DRC Style, DRC Fast, and DRC Style, DRC Full. So, moving on to the second challenge of the lab exercise, which is to find a missing or incorrect rule that needs to be fixed. Rule NWell.4 on the same layout is one such example. The rule is stated as all NWells will contain metal contacted tap. Rule checks only for L icon on tap. What this means is that every NWell must have an N-tap layer contact, which in Magic is called N-substrate N-contact or NSC, inside it somewhere. Since there's no distance associated with the rule, it's impossible to write this as a simple edge-based DRC rule, but it does lend itself to a CIF output rule very easily. The general idea of the rule is this: take all N-tap contacts and expand to fill the area of any NWell underneath. For that, there's a CIF output operator called bloat-all, and you can look up the syntax on the Magic website. After applying the bloat-all operator, you have a set of all NWells that contain taps. So all you have to do is take the set of all NWells and remove the set of all NWells that contain taps, and whatever is left over is an error. I'll start with creating the Magic DRC rule, which is simple. I'll copy a CIF max width rule, change the name of the layer to something new, say NWell_untapped, and rewrite the rule text for it, like so. Now I go to the CIF output section style DRC. I can't think of a way to do it in one temp layer, so I'll first create a temp layer called NWell_tapped. The layer uses a simple bloat-all operator that takes all layers NSC, which is the N-tap contact, and expands it to fill any NWell that is underneath it. Now I create a second temp layer called NWell_untapped, which starts with all NWell geometry and subtracts all NWell_tapped geometry, leaving only those NWells that are not tapped. Finally, I'm going to go back to my DRC rule and wrap it in variance full on top and variance star on the bottom. That means that this rule is only checked when the DRC style is DRC full. All rules below it are checked for all DRC styles. That keeps this rule check from being a burden on the interactive DRC. So, does this work? Let's check. I'll save the tex file and then do another tex load command. First, I'll do DRC check. No errors appear, which is correct. The default style is set to DRC fast, and I didn't want the rule checked for DRC fast. So now I'll change the style to DRC full with the command DRC style DRC full. Again, nothing happens because the DRC is not automatically rechecked just because the rule style changed. Now do DRC check. And now I get an error over the whole NWell because it isn't tapped. But is the rule correctly implemented? I have to check the opposite case too. So I'll draw a second endwell, which immediately gets flagged, of course. Then I'll put a tap contact in it, and the error goes away. So, problem solved. Note that implementing this rule means that all the bare endwells in the diagram get flagged, so they'll all need to get tap contacts to make the whole page correct again. Also note that even the Skywater rule implemented in Caliburn does not attempt to make an electrical check. Placing a contact in the endwell and not connecting it to anything would violate the spirit of the rule, so to speak, even though it would pass DRC in both Calibre and Magic. It is very hard to implement rules that essentially need to know how a circuit works before it can tell if there's a rule violation or not. Some of this remains up to the designer or maybe to other tools to check and make sure that there are no problems in the layout. Now it's up to you to find a problem, a rule that is either unimplemented or implemented incorrectly and requires a complex solution with layers generated through SIF output operators. Then go solve it. Maybe the hardest part of this exercise is figuring out what kind of a rule isn't possible to represent with the simple edge-based DRC rules. While you're working on that, here are a few things to watch out for. First, some rules are unimplemented because there are no layers yet to represent them. In particular, the UHVI, the ultra-high voltage implant layer, is not represented in Magic, so rules involving UHVI cannot be implemented until it is. Second, some layers like N+ implant and P+ implant layouts, NSD and PSD respectively, are automatically generated and can only be viewed in Magic using SIF-C N+ or SIF-C P+, respectively. Make sure you've selected the right DRC style when trying to view them. The rest of this lab is up to you, so good luck, and remember that you are helping out the Google Skywater OpenPDK effort. Thank you.